Welcome and thank you for joining the Sleepy Scientist tonight. These videos are made to help you wind down, relax and drift gently towards sleep, all while filling your mind with calm wonders of the universe. Tonight we're exploring one of the oldest and most mysterious questions of all. Where does space stop, and does it ever truly end? Before we drift too far into the cosmos, I'd love to know, where in the world are you listening from, and what time of night is it for you? It's always fascinating to see where in the wide world these quiet journeys are being heard. If you enjoy this calm exploration, please consider giving the video a like and subscribing to the channel. If you're already subscribed, thank you so much for supporting these sleepy science stories, and kindly tap the little notification bell so you won't miss the next gentle voyage into the unknown. I do hope the video isn't so interesting that it keeps you awake, but if it does, at least the mysteries of the universe will have been your bedtime reading. So does the universe come to an edge, or is it endless? Let's drift into the question together. The idea of space ending is one of those puzzles that has lingered in human thought for thousands of years. Philosophers, astronomers, and poets have all asked in their own ways, if you could travel far enough, would you reach a boundary, a wall, or perhaps a doorway to something else? Or is the universe without limits, stretching forever in all directions with no edge at all? This question is not just about distance, it is about the very shape and nature of reality. To wonder where space might stop is to ask what kind of cosmos we live in, finite or infinite, closed or open, bounded or boundless. It is also to face the limits of what we can ever know, because the universe places horizons on our sight and understanding. In this journey we will step carefully through the ideas that shape this question. We will begin with the simple notion of an edge, and why our everyday sense of it may mislead us when applied to space. We will look at the difference between the observable universe, the part we can see, and the universe as a whole, which may be vastly larger. We will explore how light, expansion, and cosmic horizons frame what is visible, and how geometry and topology hint at whether space could be finite without borders or infinite without end. Along the way, we'll use gentle analogies to picture the cosmos: spheres, surfaces, light cones, and cosmic webs, each a model to stretch the imagination without overwhelming it. We will touch on the science of inflation, the role of dark energy, and the way astronomers use the cosmic microwave background to search for signs of repetition or curvature. We'll also pause for philosophy, because questions of infinity and limits are as much about thought as they are about measurement. This exploration is not meant to give a single final answer, because science itself does not yet have one. Instead, it is an invitation to drift through possibilities, to understand what is known, and to appreciate the quiet vastness of what remains unknown. So as you settle in, breathe deeply, and let the day fade, imagine yourself standing at the farthest edge of sight, staring outward into the night. What lies beyond the horizon we cannot cross? Is there a boundary, or does the universe simply keep unfolding forever? When we hear the word edge, the mind immediately calls up familiar images. A cliff face dropping suddenly into the sea, the sharp rim of a coin, the point where the land stops and the ocean begins. In everyday life, edges are boundaries, places where one thing ends and another begins. They are comforting in their clarity. You know exactly when your foot leaves solid ground and finds empty air, or when the line of paint stops at the corner of a wall. But when we take this everyday notion of edges and apply it to the universe, the image quickly starts to wobble. The universe is not a field or a sheet of paper with a neat perimeter we could simply step across. When people first began to imagine the cosmos in ancient times, it was natural to picture it as a kind of dome or shell. Some traditions spoke of the heavens as a solid sphere surrounding the earth, studded with stars like gemstones. Others imagined it as a cosmic tent, with the sky stretched overhead and the ground beneath our feet. In those models, the edge was literal, like the lid of a jar. Beyond it, there might be nothing at all, or perhaps some unknown substance or divine realm. The problem is that modern science has shown us space does not behave like a container. It is not a box with walls, nor a stage on which galaxies and planets move like actors in a play. Instead, space is better thought of as a web of relationships. General relativity, Albert Einstein's great theory of gravity, tells us that what we call space is woven together with time into a single fabric, space-time. This fabric bends and curves depending on the presence of matter and energy. Galaxies, stars, planets, even your body, all of these bend space-time a little, and it is this bending that we experience as gravity. So if space is not a container, what happens to our idea of an edge? If there is no wall to bump into, then asking where the universe ends becomes trickier. Imagine you're walking in a field on a foggy night. You can only see a few steps in front of you, but the ground continues whether you see it or not. The visible horizon is not the end of the field, it is simply the end of what your eyes can detect in the mist. In a similar way, the observable universe is not necessarily the limit of all that exists. It is just the limit of what light has had time to reach us since the beginning of cosmic time. Edges can be thought of in at least two different senses. One is an edge in space, a physical boundary beyond which there is nothing. The other is an edge in time, a moment before which the universe as we know it did not exist. These are very different concepts, but they often become tangled in conversation. When someone asks, "What's at the edge of the universe?" they might mean a spatial boundary, like the rim of a balloon. But they might also be brushing up against the question of beginnings. What came before the Big Bang, and does the past have an outer limit? To see why this distinction matters, think of a map. If you have a map of an island, the coastline is an edge in space. You step past it and you're in the ocean. But if you have a timeline of a person's life, the first entry, birth, is an edge in time. There is no wall there, only the fact that the record does not extend earlier. The cosmos might have neither kind of edge, or it might have one but not the other. It could be finite in age but unbounded in extent, or it could go on forever both in space and in time. Each possibility raises its own puzzles. General relativity gives us a way of framing these puzzles without assuming that space must behave like a box. Because space is defined by the distances between objects, to speak of a boundary to space is to ask whether those relationships themselves can come to a halt. If you imagine all galaxies suddenly vanishing, you would also erase the very concept of space, because there would be no distances left to measure. In that sense, asking what lies outside the universe is a little like asking what is north of the North Pole. The question uses words we understand, but the combination creates a picture that does not really make sense. Still, our brains crave edges. They help us navigate the world. To live in an infinite, edgeless expanse is something most people find deeply unsettling, perhaps because it has no anchor. So we borrow metaphors from everyday life, walls, shells, balloons, to make the idea manageable. They are useful, but they must be handled with care, because they can suggest limits that may not exist. It is worth pausing to reflect on how strange it is that we're even able to ask such a question. A species on one small planet, orbiting one average star, wonders not only about what lies across the sea or beyond the horizon, but about the furthest reach of existence itself. The question of edges is both scientific and philosophical. Scientifically, we can define horizons, measure distances, and test whether space is curved or flat. Philosophically, we wrestle with the implications. What does it mean to exist in a universe without boundaries, or one with boundaries we can never reach? There is also something playful in all this. Imagine walking and walking in one direction, determined to find the edge. If the universe is infinite, you will never succeed. If it is finite but unbounded, like the surface of a sphere, you will eventually return to where you began without ever finding a wall. In both cases, the journey continues without an edge. The only real edges you encounter are those of your own endurance, or perhaps the soles of your shoes. So when we speak of the edge of the universe, we are really asking a cluster of questions. Is there a spatial boundary? Is there a temporal beginning? Or are we simply limited by what we can observe, like travellers lost in fog who cannot see the full extent of the land they walk on? These are the senses in which the universe might or might not have an edge, and each sense points us toward a deeper understanding of what it means to live in a cosmos where distance and time are not fixed backdrops, but active players in the story. By beginning with the simple word edge, we uncover a wealth of complexity. What feels obvious in daily life becomes subtle when applied to the universe as a whole. The cliff face and the coastline are easy enough to locate, but the cosmic edge, if it exists, may be something stranger, or perhaps nothing like an edge at all. And that is where the true wonder lies, in a universe that challenges the very language we use to describe it. When people talk about the size of the universe, they're usually thinking of something very specific, the observable universe. This is the part of the cosmos from which light has had time to reach us since the beginning of cosmic history. Because light does not travel infinitely fast but at a finite speed, albeit an impressively quick one of nearly 300,000 kilometers per second, we only receive information from regions within a certain distance. Anything farther away is, at least for now, invisible. The idea is easier to grasp with simple thought. Imagine standing in a dark forest at night with a lantern. The glow stretches only so far before fading into blackness. The forest does not end where the light stops, but your visible world does. The observable universe is like that lantern glow, except that instead of light spreading outward, it is light streaming inward toward us, and the limit is set not by weakness of the beam but by the passage of time. If the universe is about 13.8 billion years old, you might expect the observable radius to be about 13.8 billion light years, since that is how far light can travel in that time. But because space itself has been expanding while the light has been travelling, the true radius is larger. The most distant galaxies we can see are now about 46 billion light years away. That gives us a bubble with a diameter of about 92 billion light years across, our personal cosmic viewing sphere. This bubble is not an edge of existence. It is what physicists call a horizon, a boundary of visibility. Just as the horizon at sea is not the end of the ocean, but merely the limit of your sight, the cosmic horizon marks the limit of what has had time to interact with us. Beyond it, galaxies may lie, stars may burn, and structures may sprawl, but their light has not yet arrived. To say, we cannot see farther, is not to say, there is nothing farther. The distinction is subtle but crucial. Too often, illustrations of the universe show the observable bubble as if it were the totality, a glowing sphere surrounded by blankness. But the blankness does not mean emptiness. It simply reflects ignorance, the fact that signals have not yet crossed the gulf. In reality, the universe almost certainly extends beyond what we can see, possibly a little beyond, possibly vastly beyond, and perhaps without limit. You might wonder, if light has not yet reached us from those distant regions, could it ever? The answer depends on the future behavior of the universe. Because space continues to expand and because dark energy drives that expansion to accelerate, many regions that are currently visible will eventually slip beyond a permanent horizon. Their light will still reach us, but after a certain point new signals will no longer get through. It is a bit like watching a ship sail away on a river with a strong current. For a while, its signal flag is visible, but eventually the current carries it so far that no fresh messages can arrive, even though the ship continues to exist. Thinking about horizons changes how we picture the universe. It reminds us that what we call the universe in everyday conversation is usually shorthand for the observable universe. That is our cosmic neighborhood, the part accessible to observation. But just as someone living in a village centuries ago might have believed their valley was the whole world, only to later discover oceans and continents, we must be cautious not to mistake our horizon for the ultimate boundary. The observable universe also depends on where you stand. Every galaxy has its own horizon centered on itself. If you were living on a planet in a galaxy billions of light years away, you would see your own sphere of observability, overlapping with ours but not identical. This fact alone hints at the greater whole, because each horizon is only a slice of the larger fabric. Astronomers often describe the observable universe as a time machine. Looking out is the same as looking back, since light from distant objects shows us how they appeared long ago. When you see a galaxy 10 billion light-years away, you're seeing it as it was 10 billion years ago. The further we look, the closer we come to the moment of the cosmic dawn. At the outermost edge of our vision, we find the cosmic microwave background, the faint afterglow left over from when the universe was only about 380,000 years old. Beyond that lies the opaque era, when matter was still too hot and dense for light to travel freely. We cannot peer through it with ordinary telescopes, though scientists are finding clever ways to probe hints from that earlier time using neutrinos and gravitational waves. It is humbling to think that what we see is not the universe as it is, but as it was. Even our nearest star, the Sun, shines on us with light that left 8 minutes earlier. The nearest large galaxy, Andromeda, sends us light that began its journey over 2 million years ago, long before humans existed. For the most distant objects at the edge of the observable universe, the light began its trek billions of years before Earth itself formed. In a sense, the night sky is a museum, each star and galaxy a fossil of light, frozen in time. Yet for all this beauty, the fact remains that our view is limited. The universe may be finite or infinite, curved or flat, but whatever its true form, we only have access to the patch defined by our horizon. That limitation is not a flaw of science, but a natural boundary imposed by the speed of light in the age of the cosmos. It is, in fact, remarkable that we can say anything at all about regions billions of light-years away, given that we occupy one tiny corner of space and one fleeting moment in time. So when we speak of the observable universe, we are naming both our grandest domain and our strictest limit. It is vast enough to humble the imagination, yet modest enough to remind us that we do not see everything. Beyond the horizon, the universe continues, whether in familiar patterns or in ways utterly alien to our experience. The lantern light ends, but the forest goes on. The next time you step outside and look at the stars, consider that you are gazing into a bubble almost 92 billion light-years across. Within that bubble lie trillions upon trillions of galaxies, each with its own billions of stars. Beyond the bubble lies the unknown, hidden not because it is absent, but because light has not yet carried its story to us. The observable universe is not the whole, but it is our window, and through it we catch just enough of the infinite to be left wondering how far the cosmos truly stretches. Imagine standing still in the middle of a wide, dark plain holding a lantern. The light spills outward in all directions, forming a glowing sphere that grows larger with every passing second. Now imagine the same process in reverse. Light from the world around you streaming inward toward your position, each ray converging on where you stand. If you trace both the outward and inward spread of this light through time, you begin to picture what physicists call a light cone. A light cone is not a literal structure sitting out in space, but a diagram that captures what can influence you and what you can influence. At its heart is the speed of light, that cosmic traffic law that no material object can exceed. Because nothing outruns light, the universe arranges itself into zones of connection and zones of separation, and the boundaries of those zones form cones. Start with the past light cone. This is the region of space-time from which signals could have reached you by now. Every star you see in the night sky, every ancient supernova whose light has only just arrived, every ripple of gravity that passes through Earth, they all lie inside your past light cone. Events outside it, no matter how dramatic, remain invisible to you because their messengers have not had time to arrive. If a galaxy lies 1 billion light-years away, you can only see events that happened there 1 billion years ago. Anything that happened more recently will still be in transit, racing through the void toward your eyes. Now flip things around and think about your future light cone. This is the region of space-time that you can influence from where you stand. If you shine a flashlight into the night, the outward stream of photons marks the growing boundary of your influence. Right now, your light cone includes the nearby trees and buildings. In a few years, it will include stars dozens of light-years away. In millions of years, it might wash across distant galaxies. The future light cone is the expanding bubble of potential contact, the zone of space-time where your existence can leave an imprint. Between these two cones, past and future, lies the present moment, which physicists call the here and now, the point where the cones touch. Everything you experience, everything you can measure or remember, fits neatly into this diagram. It is the universe's way of organizing cause and effect. That brings us to causality, the great cosmic referee. Causality ensures that effects follow causes and that no information travels faster than light. Without causality, the universe would be chaos, signals arriving before they were sent, consequences preceding actions, events unraveling into paradox. Fortunately, the light cone structure prevents that. If two events are outside each other's light cones, neither can affect the other, no matter how hard they try. It is as if the cosmos has installed polite waiting lines, ensuring no one cuts ahead in time's orderly queue. This might sound abstract, but light cones explain why our universe feels the way it does. Consider two distant galaxies separated by many billions of light-years. At this moment, they might be too far apart to ever exchange signals, because the expansion of space carries them away faster than light can bridge the gap. They fall outside each other's future light cones. To us, that means they are causally disconnected. What happens in one has no effect on the other, at least not from this moment onward. The universe, vast as it is, divides itself into regions that can never talk to each other. On a smaller scale, the same principle applies. If you drop a pebble into a pond, ripples spread outward in circles. Only points on the water within the expanding ring are affected. In space-time, the expanding ring is three-dimensional and shaped like a cone, with time stretching upward. The ripples of causality only touch what lies inside. The beauty of this framework is that it also defines what we mean by the end of observation. When we say we cannot see beyond the observable universe, what we really mean is that the past light cone of our present moment does not extend far enough to include those regions. They exist outside our cone, unreachable until more time passes, if they are reachable at all. The limit is not imposed by walls or barriers, but by the geometry of light cones. Think about a distant star whose light has not yet reached us. Right now, that star lies outside our past light cone. In 1 million years it may slip inside as its photons finally arrive. But there are also stars and galaxies whose light will never enter our cone, because the accelerating expansion of the universe ensures the gap between us grows too fast. In those cases, the end of observation is permanent, a horizon written into the future shape of space-time. This way of looking at things shifts the meaning of where space stops. Instead of thinking about running into a cosmic wall, we understand that the stopping point is defined by where the signals fit inside our cone. It is not space itself that ends, but our ability to share connections across it. What is beyond the cone remains real, but it is sealed off from us, as though placed behind a curtain that can never be lifted. Even black holes can be explained this way. Their famous event horizons are simply light cones tipped inward. Once you cross that horizon, your future light cone points entirely toward the singularity. No matter how much you struggle, all possible paths forward end in the same place. The edge of a black hole is not a physical surface but a reshaping of cones, a rearrangement of cause and effect. The same idea applies on the larger scales. The cosmic horizon that marks the boundary of our observable universe is also defined by cones. It is the line where signals cannot make it to us in time, no matter how long we wait. In both cases, black holes and the cosmos, the edge is not a wall but a consequence of how light and time interact. It is tempting to imagine some omniscient being outside our universe watching it all at once, free of cones and horizons. But even that thought is misleading, because the cones are not obstacles laid on top of space-time. They are space-time itself. They are the structure of reality, not a limit imposed from outside. To remove them is to remove the very stage on which the universe unfolds. All of this might sound daunting, but it has a surprisingly gentle takeaway. Light cones show us that while the universe may be infinite, our personal connection to it is always finite, defined by the signals that can reach us and the ones we can send. We exist inside a shifting bubble of contact, carried along in the flow of time. Beyond that bubble, the cosmos stretches on, untouched by us and untouching us. And yet within the cone we find everything we know. The stars, the galaxies, the story of the past and the possibilities of the future. So when you look up at the night sky, remember that you are gazing into your past-like cone, catching whispers from across billions of years. And when you shine a light, know that you are extending your future cone outward, leaving a trace of your presence that will ripple into the darkness long after you're gone. In this sense, cones are not confining. They are the delicate architecture that makes experience possible, a reminder that what we call the end of space is really just the edge of what can ever reach us. When people hear that the universe is expanding, it is natural to imagine galaxies rushing outward through some kind of cosmic void, as though an enormous explosion had hurled them away from a central point. It is an image drawn from everyday experience. Firecrackers scatter sparks, balloons burst with shreds flying outward, ripples spread across a pond. But the expansion of the universe is not like that. There is no central point, no outer space into which everything is racing. Instead, what grows is space itself. The distances between galaxies stretch, not because they're flying through something, but because the very fabric that measures those distances is expanding. To see this more clearly, consider the raisin bread analogy. Imagine a ball of dough sprinkled with raisins. As the dough rises in the oven, every raisin moves farther away from every other raisin. From the perspective of any single raisin, it looks like all the others are receding, and the farther a raisin is, the faster it appears to move. That is because there is more dough in between to stretch. This is roughly what happens in the cosmos. Galaxies are like raisins and space is like the dough. The analogy, however, has its caveats. Unlike bread dough, the universe is not rising in a pre-existing kitchen. There is no oven, no background space into which it is swelling. The bread itself is all there is. The expansion does not need an outside container. That is one of the hardest things to wrap the mind around. We're used to objects expanding into something larger, but the universe is simply all there is, and its expansion is a change of scale within itself. This distinction matters because it reshapes the way we think about cosmic growth. If the galaxies were racing through an empty void, we might expect to find a central explosion point where it all began. But no matter where you stand in the universe, you see other galaxies receding from you. There is no privileged center, no cosmic origin spot. Every galaxy sees the same broad pattern, because what expands is not their motion, but the metric, the ruler itself that defines distance. This is called metric expansion, and it is one of the signature insights of general relativity. Metric expansion also explains why light from distant galaxies is redshifted. When light travels through space, its wavelength stretches along with the expansion. This makes the light appear shifted toward the red end of the spectrum. It is not that galaxies are roaring away like cars speeding down a highway. Instead, the road itself is stretching under them, and the photons of light elongate as they travel along. That is why the redshift increases with distance. The farther the light has travelled, the more stretching it has undergone. A common misunderstanding is to picture galaxies as objects tearing through space at breakneck speeds. In reality, most galaxies are not moving through space very fast relative to their local neighbours. On smaller scales, galaxies cluster, orbit and collide under their own gravitational pulls. But on the grandest scales, the observed recession is not motion through a medium, it is the medium itself changing. Space stretches, and the galaxies go along for the ride, like passengers sitting in place as their seats slide farther apart. The balloon analogy is another popular way of imagining this. Picture dots drawn on the surface of a balloon. As you inflate the balloon, the dots move away from each other. No dot is the center of the expansion. The whole surface grows and every dot sees every other dot receding. The surface of the balloon has no edge, yet it is finite. The downside of this picture is that it tempts us to think of the universe expanding into the larger air-filled room. In reality, there is no larger room. The balloon surface is all there is, just as our universe may be all there is. The embedding space is only in the analogy, not in reality. Understanding expansion as metric stretching also helps explain why some galaxies appear to recede faster than the speed of light. At first, this seems to break the cardinal rule that nothing can exceed light speed. But the rule applies to objects moving through space, not to the growth of space itself. When the metric expands, distances can grow so quickly that faraway galaxies slip away faster than light could bridge the gap. No law is broken, because nothing is moving through space faster than light. It is space itself that is enlarging between us. This is a deeply counterintuitive idea, and it has taken humanity a long time to accept it. Early in the 20th century, when Edwin Hubble showed that galaxies were receding in proportion to their distance, the natural interpretation was motion outward. It was only through the lens of Einstein's general relativity that scientists realized a deeper truth. The fabric of space-time itself is dynamic, capable of stretching, bending, and evolving. The galaxies are not projectiles in a cosmic blast. They are beads on a stretching thread. To ground this in something more familiar, think of measuring distance with a rubber band ruler. Suppose you mark ticks on a rubber band at regular intervals, then slowly stretch it. If you measure the distance between two objects placed along the rubber band, the number of ticks between them increases, even though the objects have not moved relative to the band. In the same way, cosmic distances grow because the ticks of space expand. The galaxies are not tearing away, the ruler is changing. The consequences of this simple fact are profound. It means the universe does not require an outside into which it expands. It means the night sky is not filled with galaxies rushing away from us like startled birds, but with galaxies calmly sitting on the expanding fabric of space-time. It also means the light from those galaxies carries a record of that stretching, a cosmic fingerprint etched in redshift. It is tempting to ask what the universe is expanding into. but the more accurate question is, how is the scale of distances within the universe evolving? The former assumes an external space, the latter respects the insight of relativity. Once you accept that space itself is flexible, the picture becomes less about motion and more about growth. And this growth is not uniform in every detail. On smaller scales, gravity resists expansion, galaxies remain bound together, stars orbit in stable systems, planets circle suns without being carried away. You're not expanding away from your chair, nor is your cup of tea stretching into thin vapor. Local forces overwhelm the gentle swell of cosmic expansion. It is only on scales of millions of light years, and beyond that expansion becomes visible. The universe expands in the large, while staying stitched together in the small. So when you hear that the universe is expanding, resist the urge to imagine galaxies zipping outward into some vast emptiness. Instead, think of the distances themselves lengthening. Think of photons elongating as they travel, their colours shifting like music played in a slower key. Think of a fabric whose weave is loosening ever so gradually, carrying galaxies farther apart without any of them having to move. The cosmos does not expand into something else. It simply expands. That is enough, and it is more than wondrous. Curvature is one of those ideas that sounds simple enough until you try to pin it down in the context of the universe. In everyday life, curves are easy to spot. A road bends to the left, a bridge arches over a river, a ball is round. We're used to thinking of curvature as something you can see by standing back and looking at the whole object. But when it comes to space itself, we cannot step outside for a view. If the cosmos is curved, we're inside the curve, woven into it, with no balcony from which to observe the shape. The key difference is that spatial curvature is not about lines bending in some external space, but about how distances and angles behave inside the universe. Imagine drawing a triangle on a flat sheet of paper. The angles always add up to exactly 180 degrees. Now draw a triangle on the surface of a sphere, like Earth. If you start at the equator, go up to the North Pole, and then back down at a right angle, you have created a triangle whose angles add to more than 180 degrees. The excess is a sign of positive curvature. On the other hand, if you drew a triangle on a saddle-shaped surface, the angles would add to less than 180 degrees, a sign of negative curvature. Physicists borrow these simple ideas and apply them to space itself. If space has positive curvature, like a sphere, it is finite but without edges. You could travel forever and eventually loop back to your starting point. If it has negative curvature, like a saddle, it stretches outward without bound and is infinite in extent. If it is flat, like an endless plane, it is also infinite, extending without limit in all directions. This is where the words flat, open and closed come in. A closed universe has positive curvature, like the surface of a sphere. An open universe has negative curvature, like a saddle. A flat universe is exactly balanced, with zero curvature. Each possibility carries profound implications for whether the universe is finite or infinite, and for how it might evolve in time. A closed universe is finite but unbounded. There is only so much space, though you will never find a wall marking the end. It is a bit like living on the surface of Earth. You can walk in one direction forever without falling off, yet the total surface area is limited. The universe might behave in a similar way in 3 dimensions. The idea is both comforting and disorienting. Comforting because it avoids the abyss of infinity, disorienting because it is hard to picture a 3-dimensional surface folding back on itself. An open universe with negative curvature would be infinite. It would also have a geometry that feels subtly strange. Parallel lines that we expect to stay the same distance apart would diverge. Large triangles would fall short in their angle sums. Such a universe has no looping paths that bring you home again, no finite volume, just an endless, expanding saddle stretching into infinity. A flat universe is the middle ground, the knife edge between positive and negative curvature. In a flat geometry, Euclid's familiar rules hold true even at cosmic scales. Parallel lines stay parallel, triangle angles add neatly to 180 degrees, and space stretches outward without bound. It is infinite, but without the odd distortions of negative curvature. For much of the 20th century, cosmologists debated which option was correct. The answer matters because curvature is linked to the overall fate of the universe. In a closed model, expansion might eventually reverse, leading to a collapse known as the Big Crunch. In an open or flat model, expansion could continue forever, though the details depend on dark energy. The shape of space sets the stage for cosmic destiny. So how do we measure curvature when we cannot step outside the universe to look? The trick is to use the oldest light we have, the cosmic microwave background, the afterglow of the Big Bang. This faint radiation carries tiny fluctuations in temperature, patterns frozen from the early universe. By studying the size of those patterns, astronomers can infer the geometry of space. If the universe were positively curved, the patterns would look larger than expected. If negatively curved, they would look smaller. If flat, they would appear just right, like Goldilocks porridge. The data, particularly from satellites like WMAP and Planck, show that the universe is astonishingly close to flat. Within the precision of our instruments, the sum of triangle angles in cosmic geometry appears to be 180 degrees. The margins of error are tiny, but they still leave room for slight curvature. It is possible the universe is very large and gently curved, either positively or negatively, but so large that the curvature is imperceptible within our observable patch. Imagine standing on Earth and trying to measure its curvature with a yardstick. Locally, it looks flat. Only when you can step back far enough does the roundness reveal itself. The near flatness of the universe is both surprising and puzzling. In fact, it gave rise to one of the great mysteries of cosmology. Why should the universe be so finely balanced between open and closed? This question helped motivate the theory of cosmic inflation, a brief episode of rapid expansion in the early universe that would have stretched any initial curvature flat, much as blowing up a balloon makes a small patch look smooth. Whether inflation is the full explanation is still debated, but the evidence for near flatness remains one of the strongest clues about the universe's early history. So what does this flatness allow? It means that within our observable region, the universe is effectively infinite. There are no signs of looping back on ourselves, no clear evidence of a finite volume. It is as though we live on an endless plane where every direction stretches out without limit. At the same time, we cannot rule out the possibility of curvature beyond our view, hidden at scales larger than our horizon. The universe might be like an enormous sphere so vast that from our perspective it looks flat, just as Earth looks flat to someone walking across a field. The everyday mind struggles with this. We know what a curved ball looks like. We know what a flat sheet looks like. But to imagine the universe as a three-dimensional closed surface, or as an infinite saddle, or as an endless flat expanse, pushes our intuition to its limits. That is why analogies are useful, even if imperfect. They remind us that curvature is not a matter of bending into some higher space, but of how geometry behaves within the universe itself. There is something quietly profound about the fact that we can measure this at all. From one small planet, using light that has travelled for nearly 14 billion years, we have traced the geometry of the cosmos with exquisite precision. Whether it is truly flat or only nearly so, the answer shapes our understanding of what kind of universe we inhabit. And it frames the deeper question: if space is finite, how large is it? If infinite, how do we live with the concept of endlessness? Curvature, in the end, is not just a matter of geometry. It is a way of asking whether the universe is bound or unbound, limited or limitless. Flatness gives us a picture of infinity, positive curvature of closure without edges, negative curvature of infinite openness. Each possibility is strange, yet each is consistent with the mathematics of relativity. For now, the evidence leans toward flatness, a universe balanced delicately between the two extremes. Whether that balance is exact or merely an illusion of scale remains one of the most fascinating questions of modern cosmology. One of the strangest but most important ideas in cosmology is that space could be finite yet unbounded. At first glance, that sounds like a contradiction. How can something have a limited size without also having a border? Our daily experience trains us to think of finiteness and boundaries as inseparable. A football field ends at the fence, a book ends at the cover, even the sea ends when you reach the shore. If something is finite, it ought to have an edge. Yet the universe might be one of those rare cases where finiteness does not come with a wall. The best way to begin untangling this is with the classic sphere analogy. Imagine you are an ant crawling across the surface of a globe. From your perspective, the world stretches out in all directions. You can walk north, south, east, or west without limit. If you keep moving, you never encounter a cliff where the surface stops. Instead, after a very long time, you return to the place you started, just as explorers eventually circumnavigated Earth. The surface is finite because it has a definite area. It is not infinite like an endless plane, but it is unbounded because it does not have edges where the surface abruptly terminates. The trick here is that the two-dimensional surface curves back on itself. The finiteness comes from the total area being limited. The lack of boundaries comes from the fact that the surface has no outer edge within its own dimensions. When we apply this reasoning to three-dimensional space, we arrive at the possibility that the universe itself could loop back on itself in a similar way. In such a cosmos, you could set off in a straight line and, after an unimaginably long journey, end up where you began without ever finding a wall or border. This possibility is hard to grasp, partly because our minds keep sneaking in an extra dimension. When you picture the globe, you're imagining it floating in space, and you see the curved surface from outside. But the ant crawling along the surface does not need that outside view to understand its world. For the ant, the surface is all there is. In the same way, if the universe is finite and closed, it does not need to be embedded in some larger external space. Its closure is intrinsic, a property of its geometry. The notion of finite yet unbounded space also challenges our sense of direction. We are used to maps with edges, with a clear boundary between what is included and what lies beyond. But if the cosmos closes back on itself, then the concept of beyond loses meaning. There is no outside the map. The whole of existence is contained within the looping geometry. That is a hard habit of thought to break, since so much of our daily reasoning is built on contrast between inside and outside. There are other intuition traps too. One is the assumption that travelling in a straight line forever always leads farther away. On a flat, infinite plane, that is true. On a sphere, it is not. Straight lines curve back eventually, a property that is built into the surface itself. Another trap is imagining that if the universe is finite, we should be able to find a place where it stops. That makes sense in our ordinary world of books, boxes, and backyards. But in curved spaces, finiteness does not imply stoppage. So how can we climb out of these traps and build a better intuition? Analogies help, though none are perfect. Think again of Earth's surface. A person in ancient times convinced the Earth was flat might have worried about reaching the edge and falling off. The discovery that Earth is a sphere removed the problem entirely. there is no edge to fall from, only a closed shape. The same could be true for space. What seems like an infinite plane with potential edges may instead be a vast closed surface without any need for a border. Mathematics provides the real key. In geometry, one can describe spaces that are finite yet unbounded with precision. The surface of a sphere is one example. More exotic possibilities exist, like a three-dimensional torus, which loops back in multiple directions. These are not fanciful inventions. They are legitimate solutions to Einstein's equations of general relativity. They describe universes in which space is finite but complete, with no edges to cross. If our universe is such a shape, what would it mean for us? In theory, light could travel all the way around and return to its starting point. You might one day see the Milky Way from behind, though stretched and distorted by the long journey. In practice, the expansion of the universe likely prevents us from ever witnessing such grand repetitions. But the principle remains. A finite, unbounded cosmos is a place where boundaries are unnecessary, where closure happens through geometry rather than walls. There is a certain elegance to this picture. It allows the universe to be self-contained, with no need for an outside or an edge. It avoids the awkward question of what lies beyond a cosmic wall. At the same time, it preserves the comfort of finiteness. There is only so much space, though. It is far more than we could ever traverse. The balance between these two ideas, limited but edgeless, has a quiet beauty. It is also humbling. We cannot easily picture a three-dimensional surface closing in on itself, just as our ant cannot imagine what it means to live on a globe while confined to the surface. We rely on analogies, but ultimately the true shape of space may be beyond our everyday visualization. That does not make it any less real. It simply reminds us that the universe is allowed to be stranger than our imagination. When you step outside at night and look at the stars, you may wonder whether you're staring into infinity or into a closed, finite loop. Both are possibilities, and both stretch the mind. If the universe is finite yet unbounded, then in every direction you gaze, you're looking not toward an edge, but along a path that may someday curve back to where you stand. You're inside a cosmos with no beyond, where everything is contained within the gentle curve of space itself. In that light, the phrase "no edge" becomes less of a contradiction and more of a revelation. The universe does not need a boundary to be complete. It can be finite without fences, whole without walls. And for us standing within it, the absence of edges is not a limitation but a liberation, freeing us from the fear of falling off and inviting us to wander in a cosmos that is both enclosed and endless all at once. Topology is one of those words that sounds intimidating at first, as if it belongs locked away in a mathematics department. Yet the core idea is surprisingly approachable. Topology is about the way shapes are connected rather than the precise way they bend or curve. Geometry asks about distances, angles, and curvatures. Topology asks about holes, loops, and how surfaces link together. You might say that geometry is concerned with measuring, while topology is concerned with reshaping without tearing. A favourite example is the comparison between a coffee cup and a donut. Topologically speaking, they are the same shape. Both have a single hole, the handle of the cup and the hole of the donut. You can stretch and deform the cup into the donut without cutting or gluing. The curves and angles change, but the essential hole count does not. To a geometer, the two shapes are different. To a topologist, they are twins in disguise. When we apply this to space itself, topology gives us an entirely new perspective. Geometry tells us whether the universe is curved positively, negatively, or not at all. Topology tells us how space might wrap around, whether it connects back to itself, and whether a finite space can exist without edges. In other words, topology answers questions of connectedness that geometry alone cannot. One of the most intriguing topological models of the universe is the three torus. Picture a square sheet of paper. If you glue the left edge to the right edge, you create a cylinder. If you then glue the top edge to the bottom edge, you get a surface that loops in both directions, a torus or a donut shape. Now extend that idea to 3 dimensions. Imagine a cube where opposite faces are joined. Step out through one wall and you re-enter through the opposite wall, like a character in an old video game. That is a 3 torus. It is finite in size, yet it has no boundaries. You can travel in any direction indefinitely, looping back again and again without ever finding an edge. This kind of space is profoundly strange to our everyday thinking. In a 3 torus universe, light could travel around and return from the other side. You could, in principle, see multiple images of the same galaxy appearing in different locations in the sky, like reflections in a hall of mirrors. If the universe was small enough, you might even see the back of your own galaxy, though it would be distorted and delayed by the long journey of light. Other compact topologies exist as well. Some resemble twisted 3-dimensional loops, others fold space in more exotic ways. Each one is finite and edgeless, providing different possibilities for how the universe might be stitched together. The beauty is that they all satisfy the rules of general relativity. They are not fantasy, but legitimate models of how space could be configured. So how would we know if our universe has such a topology? Astronomers look for topological signatures in the sky. One clue would be repeating patterns in the cosmic microwave background, the ancient afterglow of the Big Bang. If space loops back on itself, then light from the same region of the early universe could reach us along different paths. The result would be matching circles or repeated structures in the microwave background map, like wallpaper patterns imprinted on the sky. Another clue would be multiple images of the same cosmic objects. If space connects back on itself, light from a galaxy could wrap around and reach us from several directions. We might mistake them for different galaxies when in fact they're copies of the same one seen at different stages in its history. Detecting such repetitions would be extraordinarily difficult, but in principle it is possible. So far, the evidence suggests that if the universe has a non-trivial topology, it must be very large. No obvious repeating patterns have been found. The cosmic microwave background appears consistent with either a flat infinite space or a very large finite one. But the search continues, because topology leaves subtle fingerprints, and with better instruments we may yet uncover them. The notion that space could be connected to itself like a video game world is more than a curiosity. It highlights the fact that our intuitions about inside and outside are not reliable guides at cosmic scales. We are so used to boundaries that we struggle to imagine a space without them, yet topology provides rigorous ways for this to happen. A 3 torus universe is finite in volume, yet a traveller within it never encounters a wall. The connection is smooth, seamless, and complete. There is also something gently humorous about living in a universe with loops. You could set out to explore in one direction, confident of new discoveries, only to bump into a familiar view from the other side. Space could be playing the longest practical joke imaginable, making us wander endlessly only to find ourselves back at home. If true, it would mean that our patch of sky is not just one window into reality, but many overlapping ones, stitched together by the fabric of topology. This way of thinking also softens the hard edges of infinity. If space is finite but wraps around on itself, then we need not wrestle with the dizzying notion of endless expanse. Instead, we have a cosmos that is complete, whole, and self-connected, without requiring boundaries or an external container. That picture is both mathematically elegant and psychologically comforting. Of course, whether our universe actually has such a topology remains an open question. Current observations favour a very large, nearly flat universe, but they cannot rule out subtle connections beyond our horizon. It may be that space is infinite and simple, or it may be that it is finite and cleverly looped, hiding its edges by eliminating them altogether. Either way, topology invites us to think differently. It teaches us that the shape of the universe is not only about curves and sizes, but about how everything is linked together, the same way a coffee cup and a donut share a hidden kinship. Our cosmos may hold connections that defy our ordinary sense of place. It is a gentle reminder that the universe is allowed to be stranger than our imaginations, and that sometimes the most mind-bending truths are also the most elegant. When you look at the night sky, you may be seeing not only into vast distance, but also along paths that eventually fold back. Perhaps, in some cosmic game of hide-and-seek, the stars above your head are also the stars behind your back, their light circling around to meet you. If so, the universe is not only vast but delightfully playful, a grand loop where outside does not exist, and the only edges are the ones we imagine. Imagine trying to look back to the very beginning of the universe. You might expect to see fireworks, a dramatic burst of light, a glowing moment of creation. But when astronomers peer as far back as possible, what they find instead is a soft, uniform glow, an ancient light that fills the sky in every direction. This light is the cosmic microwave background, often shortened to CMB, and it is one of the most important discoveries in the history of science. This CMB is sometimes described as the afterglow of the Big Bang, but a more precise image is that of a fog lifting. In the earliest moments, the universe was a hot, dense plasma, with matter and radiation bound tightly together. Light could not travel freely because it was constantly being scattered by electrons. The universe was opaque, glowing but impenetrable. About 380,000 years after the beginning, everything cooled enough for electrons and protons to combine into neutral atoms. With no free charges to block their way, photons were finally released to travel across the cosmos. That moment is called recombination, and the light from it still streams toward us today, stretched into microwave wavelengths by billions of years of expansion. This makes the CMB a kind of backlit fog, the earliest visible surface we can ever see. It is not the beginning itself, but the first clear snapshot of the universe. By studying it, scientists can reconstruct the conditions of the early cosmos, its temperature, density, and even its geometry. What appears at first to be a uniform glow is in fact peppered with tiny variations, slight differences in temperature, only a few parts in 100,000. These faint ripples carry enormous information because they are the seeds of all later structure: galaxies, stars, planets, and life. The CMB also acts as a map of topology. If the universe is finite and wraps back on itself, then light from the same region of the early cosmos might reach us along different paths. Imagine standing in a mirrored room. You see multiple reflections of the same object, arriving from different directions. In the same way, a finite self-connected universe could produce repeating patterns in the CMB sky. These patterns would appear as matched circles, pairs of circles on opposite sides of the sky with identical ripples. Detecting such circles would be like catching the universe in the act of looping back on itself. Searching for these signatures is a delicate task. The CMB is faint and the ripples are subtle. Satellites like COBE, WMAP, and Planck have mapped it with extraordinary precision, revealing its texture and detail finer than ever before. Scientists comb through these maps, looking for evidence of repeating motifs that would betray a finite topology. So far, no definitive matched circles have been found. The data are consistent with an infinite flat universe, or with a finite one so large that the repetitions fall outside our observable horizon. But the search continues, because even a negative result helps narrow the possibilities. What would it mean if matched circles were discovered? It would be a breathtaking revelation. It would prove that space is finite and that it connects back on itself. We would know that the cosmos is not an infinite stretch, but a closed, self-contained structure. Light looping around would confirm that there is no outside to space, only a grand looping inside. It would also mean that the universe we see is in some sense repeating. The same patch of primordial plasma would appear in multiple directions, an echo of its own existence. Even without circles, the CMB tells us something about the scale of the universe. The very fact that we do not see obvious repetitions suggests that if the cosmos is finite, it is at least as large as the observable universe, and likely much larger. To borrow an earthly analogy, if Earth were the size of a small village, you could walk around and quickly discover its curvature. But if it were the size of a continent, you could wander for a lifetime and still be convinced it was flat. The CMB shows us that the universe, whether finite or infinite, is vast enough that our observable bubble does not wrap back in any obvious way. There is a poetic irony in this. The CMB is a faint ancient whisper, photons set free nearly 14 billion years ago, yet it tells us about the largest scales possible. From tiny ripples in microwave light, we learn whether the universe is finite or infinite, flat or curved, simple or connected. It is like reading the entire biography of a person from the faintest childhood memory. The study of the CMB has already revolutionized cosmology. It confirmed the Big Bang model, revealed the age of the universe, and measured the composition of matter and energy with remarkable accuracy. It showed us that most of the cosmos is made not of ordinary matter but of dark matter and dark energy, and it continues to act as a testing ground for new theories, from inflation to topology. Yet for all its scientific power, the CMB is also quietly beautiful. Step outside on a dark night, and though your eyes cannot see it, the ancient light of the CMB is washing over you. Every point in the sky glows with it, uniform and omnipresent, a reminder that the entire universe was once a single, glowing fog. The air you breathe and the ground you walk on are bathed in photons from the dawn of time, still carrying their story across billions of years. Whether or not the CMB ever reveals matched circles or repeating patterns, it already teaches us a profound lesson. The universe does not hand over its secrets all at once, but through faint traces and subtle clues. To find meaning in the CMB is to accept that even the quietest background can be full of information, waiting for a careful ear. It tells us that space may be finite, or it may be infinite, but either way it is deeply interconnected, stitched together by light that has travelled since the beginning. So the next time you look up at the night sky, remember that beyond the stars, beyond the galaxies, there is a deeper light, a relic from when the cosmos itself was young. It is a light that does not illuminate the ground beneath your feet, but the shape of the universe itself. It is the universe's own map, drawn in the faintest strokes, waiting for us to learn how to read it. The story of the universe begins not just with expansion, but with an almost unthinkable burst of it. Cosmologists call this inflation, and it is one of the most dramatic chapters in cosmic history. For a fleeting fraction of a second, the universe expanded faster than anything we can easily imagine, stretching from subatomic scales to macroscopic size in less time than it takes light to cross a single proton. It was expansion on fast forward, an event so quick and so extreme that it left behind a universe smoothed and sculpted into the form we see today. The idea of inflation was first proposed in the early 1980s to solve a few nagging puzzles about the Big Bang. One puzzle was the horizon problem. Why does the universe look so uniform in every direction, with the same temperature and density, even across regions that should never have had time to communicate? Without inflation, the cosmos appears too evenly mixed, as though different rooms in a mansion somehow agreed on the same thermostat setting despite never sharing air. Inflation solves this by shrinking the early universe down so small that all regions were once in close contact, able to exchange heat and settle into equilibrium. Then inflation stretched that tiny smooth patch into the vast cosmos we inhabit. Another puzzle was the flatness problem. Observations show that the geometry of space is very nearly flat, balanced delicately between positive and negative curvature. Without inflation, it is difficult to explain why the universe did not veer dramatically one way or the other over billions of years. Inflation acts like an iron, pressing out the wrinkles of curvature. No matter what the initial shape was, the rapid stretching makes it appear flat within the observable region, just as blowing up a balloon makes a small patch look smooth and straight. Inflation also explains why the universe is so large. The visible cosmos is about 92 billion light-years across, far bigger than what a non-inflating Big Bang could comfortably produce in its available time. Inflation provides the rapid growth needed to set up such a vast stage. But importantly, what we call the observable universe is only a small patch of whatever inflation created. It is the part we can see, bounded by the speed of light and the age of the cosmos. Inflation ensures that patch is smooth and uniform, but it does not tell us how far the stage extends beyond our view. You can think of it like baking bread. Suppose you start with a small lump of dough containing raisins. After a few minutes in the oven, the dough is expanded and the raisins are farther apart. Your kitchen counter may only show a slice of the loaf, but you know the rest continues beyond what you can see. Inflation is like that first explosive rise, turning a minuscule lump of space-time into a loaf vast enough to dwarf any local patch. Our observable universe is one slice of that cosmic loaf, no more and no less. A common misconception is that inflation proves the universe must be infinite. It does not. Inflation ensures that the observable patch is smooth, flat and large, but whether the whole universe is infinite or merely very large depends on details we cannot yet measure. If inflation lasted only a brief moment, the universe might be finite though still enormous. If it lasted longer, the universe could be so vast as to appear infinite from our perspective. In some versions of inflation theory, the process never ends everywhere at once. Instead, some regions keep inflating while others settle down, producing a multiverse of bubble-like patches. That scenario suggests the cosmos may be infinite in extent, but it remains speculative, far beyond what we can test directly. The key point is that inflation sets the stage for what we can observe, but does not guarantee what lies beyond. It stretches our local patch into the shape we see, ironing out wrinkles and providing the uniformity we measure in the cosmic microwave background. But the rest of the cosmic loaf may have properties we cannot access, because light has not had time to cross it. Our bubble of observation is bounded, not because space ends, but because time limits what signals have reached us. Inflation makes that bubble big and tidy, but it does not answer the question of whether the bakery itself is endless. One of the most fascinating consequences of inflation is the way it seeds structure. While it smooths out the large-scale wrinkles, it also amplifies tiny quantum fluctuations, stretching them across cosmic scales. These fluctuations became the ripples we see in the cosmic microwave background, and eventually grew into galaxies, clusters, and the grand cosmic web. Without inflation, it is hard to explain how such large-scale order could arise from such small beginnings. With it, the origin of structure is a natural consequence, a kind of side effect of the stretching process. The elegance of inflation is that it explains so much with one idea. Uniformity, flatness, largeness, and the seeds of structure all follow from this brief episode of runaway expansion. It is like discovering that one short scene in a play explains all the strange twists and turns that come later. But elegance is not the same as proof. While evidence strongly supports inflation, especially the detailed patterns in the cosmic microwave background, it is not confirmed in every detail. Scientists continue to test its predictions, searching for subtle fingerprints, such as certain patterns of polarization in ancient light that would betray gravitational waves from the inflationary era. For now, inflation remains the best explanation we have for why the universe looks the way it does. It tells us why the patch we see is smooth, why it appears flat, and why it is so vast. But it leaves open the most tantalizing question of all. How far does the patch extend? Is it merely a local stretch in a finite cosmos, or is it part of an endless expanse? Inflation itself does not decide. It gives us a stage to live on, but the size of the theatre remains a mystery. When you stand under the night sky, you're looking at the product of that ancient stretching. The galaxies are scattered across space because inflation made room for them. The cosmic microwave background glows with uniformity because inflation ironed out the early chaos. Yet beyond the horizon, there may be regions forever hidden, places that inflation shaped, but that no telescope will ever reach. Inflation explains the patch we can see, but it also reminds us that the visible is not the whole. The universe may be finite, or it may be infinite, but either way it is larger than our lantern of observation can illuminate. So inflation leaves us with a blend of certainty and mystery. We know why our local cosmos is so smooth and flat, why it is so large and orderly. But we do not know the true size of the stage, or whether the curtain ever falls. Inflation shows us the visible patch, but it does not tell us if beyond that lies a closed loop, an infinite plane, or something stranger still. It is both an answer and an invitation, smoothing the wrinkles we can see while leaving us to wonder about the parts forever out of sight. For most of the 20th century, astronomers thought the expansion of the universe was slowing down. It seemed natural. Gravity pulls things together, so the combined tug of all galaxies and all matter should gradually break the outward rush. The big question was whether that deceleration would someday bring expansion to a halt, causing the universe to collapse back in on itself, or whether it would continue expanding forever at an ever-diminishing rate. Either way, the expectation was that gravity would be the main player shaping the cosmic future. Then came the surprise. In the late 1990s, two teams studying distant supernovae found that those exploding stars were dimmer than expected. The light had travelled farther than their models predicted. The conclusion was inescapable. The expansion of the universe is not slowing down at all. It is speeding up. Instead of pulling everything back together, some mysterious component of the cosmos is driving galaxies apart faster and faster. This became known as dark energy, a name that admits we know very little about what it actually is. Dark energy makes up about 70% of the total energy budget of the universe, yet it remains one of the greatest mysteries in physics. It is not ordinary matter, it is not dark matter, and it is not radiation. The best current guess is that it behaves like a property of space itself, a kind of energy density that does not thin out as the universe expands. The more space you have, the more of this energy fills it, creating a feedback loop that accelerates expansion. It is as though space has been fitted with a cosmic accelerator pedal, and it is pressed down just enough to keep galaxies drifting farther and farther apart. This accelerating expansion leads to a strange and bittersweet idea: the future cosmic horizon. Just as the finite age of the universe creates a limit on how far back we can see, the accelerated expansion creates a limit on how far into space we can ever reach. As galaxies recede faster and faster, some will eventually cross a threshold beyond which their light can no longer catch up to us. No matter how long we wait, no matter how powerful our telescopes, signals from them will never arrive. They will slip out of our communicable future, not because they cease to exist, but because the stretching of space outpaces any attempt at connection. This event horizon of the future is different from the one that defines the observable universe today. The current horizon marks how far back we can see, set by the age of the cosmos. The future horizon marks how far forward we can talk, set by the accelerating pace of expansion. It is not a wall but a farewell line, beyond which galaxies drift into silence. Imagine standing on a shore watching ships sail away. At first, they shrink slowly, sails dipping lower on the horizon. But then, as the current quickens, the ships move faster and faster until they disappear beyond sight. You know they're still out there sailing, but they no longer belong to your world of experience. That is what happens to galaxies as they cross the future horizon. They do not vanish, they simply slip beyond our reach. The scale of this cosmic separation is immense. Billions of galaxies that are visible to us today will eventually depart forever, carried beyond the event horizon created by dark energy. In the unimaginably distant future, only the galaxies in our local group, those gravitationally bound together, will remain visible. The Milky Way and Andromeda, destined to merge into a giant elliptical galaxy, will form an island of stars adrift in darkness. Beyond that island, the rest of the cosmos will fade from view, leaving future astronomers stranded in a lonely universe with no evidence of its grander scale. There is something quietly poignant about this. We live in a privileged era when the universe is old enough to have produced galaxies, stars and planets, yet still young enough that the wider cosmos is visible. In the far future, the cosmic microwave background will fade below detectability and distant galaxies will slip away. The clues we have gathered about the true nature of the universe may be inaccessible to civilizations billions of years from now. For them, the sky will tell a smaller, lonelier story. But this fading horizon is not an ending in the dramatic sense. The galaxies do not blink out of existence when they pass the line. They continue on their journeys, full of stars and perhaps even life, but they are forever cut off from us. Ending, in this context, is a limit on communication, not on being. The universe continues to expand, continues to create new space, continues its story. It is just that our chapter becomes sealed from the others, a closed book drifting away on the tide. This reframes the question of where space stops. From one perspective, space does not stop at all. It grows faster than ever, an endless unfolding. From another perspective, our accessible universe shrinks, as fewer galaxies remain within our communicable reach. The end is not at the edge of space, but at the edge of connection. Even black holes provide a helpful comparison. An event horizon around a black hole does not mark the end of space-time, but the end of signals that can escape. The future cosmic horizon is the same on a grander scale. It is not the end of galaxies, but the end of their messages to us. They fall silent, not because they are destroyed, but because the universe's expansion stretches the line of communication beyond breaking. This picture may feel melancholy, but it also has a gentle poetry. It reminds us that our place in cosmic history is fleeting and precious. We happen to exist at a time when the wider universe is still visible, when the great web of galaxies still stretches across our night sky. We are witnesses to a cosmos in full bloom, before it fades into the solitude of the far future. So dark energy, while mysterious, teaches us something profound. It tells us that the end of space for us is not a wall, but a horizon of farewell. Galaxies slip away, not into nothingness, but into silence. The universe does not end. It simply expands beyond our reach. And in that quiet truth lies a lesson. Endings are not always about absence, but about limits. The cosmos will continue, even when our window onto it closes. It is up to us, in this rare moment when the view is still open, to marvel at what we can see and to cherish the fact that the horizon has not yet slipped too far from sight. It is one of the most common questions people ask when they first hear that the universe is expanding. Into what is it expanding? The question feels natural, even unavoidable. When a balloon inflates, it expands into the air around it. When a ripple spreads across a pond, it expands into the rest of the water. Surely then, the universe must be swelling into some kind of larger space. Surely there must be an outside, some cosmic room that contains the whole affair. But this is a trick of our intuition. The expansion of the universe is not like a balloon inflating into a room, or an explosion pushing outward into empty air. It is the expansion of space itself, not into something else. There is no outside to the universe, no rim it is racing toward. Expansion means that the distances between galaxies grow over time, not that galaxies are rushing into a pre-existing void. It is a stretching of the fabric itself, not a journey into another place. The balloon analogy is helpful up to a point. Imagine dots on the surface of a balloon. As the balloon inflates, every dot moves away from every other dot. No dot is the center, and no edge exists on the surface itself. From the perspective of a two-dimensional being living on that surface, the universe expands, but there is no outside. The analogy breaks down when we are tempted to imagine the balloon in a room, expanding into air. That outside is not part of the analogy. It is just a crutch for our three-dimensional brains. In reality, the universe does not require an external space. The expansion is intrinsic, a growth of distances within the cosmos itself. Physicists sometimes use embedding diagrams to help explain this, and they are useful as teaching tools. You might see a picture of a curved grid bending down like a trampoline under a heavy ball. The ball represents a star or planet bending space-time, while the grid represents the fabric of space. Or you might see a two-dimensional balloon representing the surface of a three-dimensional expanding universe. These diagrams are not literal. They embed lower dimensional surfaces into a higher dimensional space so that we can visualize curvature or expansion. But the higher space is only in the picture, not in reality. The surface of the balloon does not need the surrounding air to exist. Space-time itself does not need a larger stage in which to perform. The difficulty comes from how our minds are wired. We live in a world of objects inside other objects. A cup sits on a table, the table sits in a room, the room sits inside a building, and so on. We instinctively reach for an outside container when something grows. When we hear that the universe expands, we automatically imagine it inflating into something larger. But the universe is not an object sitting inside a box. It is the box itself. And asking what lies outside the box is like asking what is north of the North Pole. The words make sense individually, but together they describe a situation that does not exist. One way to see this is to think about the meaning of coordinates. In mathematics, the coordinates of a point tell you where it is relative to the system you have defined. If the universe contains everything, then coordinates only exist inside it. There is no coordinate system outside because there is no outside. The very concept of position relies on space, and space is the thing that is expanding. Beyond it, there is nothing for the word position to latch onto. This does not mean there could not be a larger reality in which our universe is just one bubble among many. Some theories of eternal inflation and the multiverse imagine such possibilities. But those are speculative and not required to explain expansion. In the standard picture, the universe does not expand into a pre-existing emptiness. It expands because the metric that defines distances changes with time. Distances increase, and that is all that is meant. Another way to frame this is to turn the question around. Ask instead, how is the distance between galaxies changing? That is what expansion measures. The galaxies are like raisins in rising bread. As the dough swells, the raisins drift apart, not because they're moving through dough, but because the dough itself is stretching. No one asks into what the bread is rising in order for the raisins to separate. The rising is intrinsic. The same is true of space. There is also no rim at the edge of the universe where expansion might be pushing into something else. In a closed, finite universe, you could travel forever and eventually loop back to where you started without ever finding a border. In an open or flat universe, you could travel forever without looping, but again without ever finding an edge. Expansion stretches these spaces without reference to an outside. The absence of a rim is not a problem to solve. It is the natural consequence of how space works in relativity. To make peace with this, it helps to embrace the strangeness. Space is not an object floating in a larger room. It is the framework that defines what room means. Asking into what it expands is like asking into what time flows. There is no riverbed for time to stream through. Time is the flow. There is no external void for space to grow into. Space is the growth. It is worth pausing to appreciate just how radical this is. For most of human history, the universe was pictured as a stage inside something larger, a dome of stars, a shell surrounding Earth, a finite cosmos bounded by walls. Only with the advent of relativity did we realize that space could be self-contained, finite or infinite, without an external container. The balloon diagrams we see today are echoes of that old intuition, teaching aids that work only so long as we remember their limits. So the next time the question arises, into what is the universe expanding, the most honest answer is, into nothing at all. It expands not into, but as. Expansion is not the growth of an object into space, but the change of space itself. That may not satisfy our craving for containers and outsides, but it is the picture that best fits the evidence. If that still feels unsettling, imagine walking endlessly in one direction. In some models of the universe, you would never find a border, never encounter a wall. You would either loop back to your starting point or continue forever into new territory. At no point would you stumble upon an edge where space gives way to nothing. The universe expands not by invading an external emptiness, but by stretching its own fabric, lengthening the distances within. In that sense, expansion is not an explosion, but a quiet unfolding, a steady change in the measure of distances. There is no outside, no rim, no container. There is only space itself, growing as time flows, carrying galaxies farther apart without moving them into anything beyond. And in that strange, elegant truth lies one of the most profound lessons of cosmology. The universe is all there is, and its expansion is not a journey outward, but a deepening of the space within. When you hear the word boundary, it is easy to picture something solid. A fence at the end of a field, a coastline where land gives way to sea, a wall that blocks the path. Boundaries in ordinary life are clear, physical, and often tangible. In general relativity, though, the story becomes subtler. A boundary in space-time is not always a wall you can bump into. It can be a feature of the mathematics, a place where the equations break down, or a genuine physical horizon where events slip forever out of contact. The trick is telling the difference. First, what counts as a physical boundary in space-time? In Einstein's theory, space-time is modelled as a smooth manifold, a continuous fabric without tiers or seams. Within this fabric, matter and energy curve space, and the geometry dictates how objects move. A boundary arises when this fabric cannot be extended any farther. Sometimes that means a true physical edge, such as the singularity at the heart of a black hole, where densities climb without limit. Other times, it means a horizon, like the event horizon of that same black hole, which acts as a one-way curtain. The horizon is not a physical wall, but it marks a limit on what signals can escape. You can pass through it without noticing, but you cannot send messages back once you're inside. Boundaries of this sort are very different from the walls and edges we encounter on Earth. They are not made of matter, nor are they obstacles you can touch. Instead, they are limits on information, lines beyond which cause and effect are reorganized. They tell you not that space has stopped, but that your access to events has stopped. That distinction is crucial. But not all apparent boundaries are real. Sometimes they are merely artifacts of the coordinates we use. A classic example is the event horizon of a black hole when written in Schwarzschild coordinates. In those coordinates, the horizon looks like a singularity, a point where the equations blow up. But this singularity is not physical. Change to a better coordinate system, and the horizon is smooth. The real singularity lies at the very centre, not at the horizon. What looked like a boundary was just a quirk of the map. It is like drawing the globe with a Mercator projection. The poles look infinitely stretched, but the Earth has no infinite poles. The distortion comes from the map, not from reality. General relativity is full of such tricks. Depending on how you set up your coordinates, you can create apparent edges where none exist, or hide edges that are truly there. That is why physicists distinguish carefully between coordinate singularities and genuine singularities. The first are artifacts of description, the second are physical limits. To separate them, one asks whether space-time can be smoothly extended beyond the suspicious region. If it can, then the edge was an illusion. If it cannot, then you have reached a true boundary of space-time. Another example is the cosmological horizon. To us it marks the limit of the observable universe, a spherical boundary about 46 billion light-years away. But this horizon is not a wall in space. Galaxies do not hit it and bounce back. It is a limit defined by time and light travel. In comoving coordinates, galaxies remain at fixed positions while space between them stretches. The horizon is simply the place beyond which light has not yet had time to reach us. Nothing dramatic happens there for the galaxies themselves. Again, the boundary exists in our frame of reference, not as a physical barrier in the cosmos. Mathematical edges and material walls differ in one other crucial way. Walls separate what exists from what does not. Beyond a garden fence, there is no more garden. Beyond the edge of a table, there is only air. In relativity, a mathematical edge may separate the region we can describe from the region we cannot, but that does not necessarily mean the other side does not exist. It may still be there, just unreachable or indescribable with our chosen coordinates. The edge is not a line between being and nothingness, but between accessible and inaccessible, describable and indescribable. This distinction changes how we think about the universe as a whole. If you imagine the cosmos as a giant sphere floating in a void, you picture a material edge. But in relativity, the edges we encounter, horizons, singularities, limits of description, are not surfaces in that sense. They are properties of the fabric itself. The universe does not need a surrounding void to press against, nor does it need a physical rim. Its boundaries are internal, defined by geometry and causality, not by brick walls at the outskirts. Even singularities, the closest thing we have to a hard edge, may not be fundamental. They are places where our equations fail, predicting infinite density or curvature. But infinities in physics are usually signs that the theory has reached the end of its domain, not that nature itself has become infinite. Most physicists believe that a deeper theory of quantum gravity will resolve singularities, replacing them with something finite and well-behaved? If so, then even the most fearsome boundaries in general relativity may turn out to be illusions created by incomplete knowledge. The broader lesson is that boundaries in relativity are more subtle than our intuition suggests. A coastline or a wall is obvious, a space-time horizon or singularity is not. They require careful analysis to separate true limits from coordinate tricks. They remind us that our maps are not the territory and that reality may be smoother than the mathematics that describes it. This can even be liberating. Instead of imagining the universe as a bubble with walls, we can think of it as a self-contained fabric, continuous and without an outside. Boundaries exist, but they are horizons of knowledge and communication, not fences in space. The observable universe is bounded by how far light has travelled, not by a cosmic wall. Black holes are bounded by the reach of signals, not by shells of matter. The edges are real but intangible, limits of influence rather than structures of substance. So when we speak of boundaries in space-time, we are really speaking of two kinds. There are well-posed edges, where space-time truly ends or becomes undefined, such as singularities, and there are apparent edges, born of our coordinates, which vanish when the map is redrawn. Learning to tell the difference is one of the triumphs of relativity. It keeps us from confusing the tricks of our language with the truth of the cosmos. Next time you hear about the edge of the universe, think not of walls or cliffs, but of horizons and limits of description. Space and time do not require material fences to be whole. Their boundaries are subtler, drawn not in bricks and mortar, but in the structure of causality. And in that subtlety lies the wonder of general relativity, a universe with edges that are not edges, boundaries that do not bound, and horizons that tell us less about endings than about the scope of what can be known. When people picture the Big Bang, the image that often comes to mind is that of a firework in the night sky, a single bright point exploding outward into surrounding emptiness. It is a natural picture, because that is how most explosions behave in our daily lives. But the Big Bang was not an explosion in space. It was an expansion of space. There was no central point where it all began, and no empty void into which it spread. Instead, every point in space was once part of the Big Bang, because the Big Bang happened everywhere at once. To imagine this more clearly, think of the surface of a balloon as it begins to inflate. The expansion does not originate from one spot on the surface. The whole surface grows together, every point moving away from every other point. There is no special centre. The same is true of our universe. The Big Bang was not a single firecracker, but a universal unfolding, with space itself stretching and carrying matter and energy along with it. This brings us to the idea of singularities. In general relativity, when we trace the universe backward in time, the equations suggest that the density of matter and the curvature of space increase without limit. If you follow this logic far enough, you reach a singularity, a point where the mathematics breaks down and ordinary descriptions stop making sense. At first glance, this seems to imply a literal beginning, a moment of infinite density and temperature, a true edge in time. But singularities are tricky. They are as much a statement about the limits of our theories as they are about the universe itself. When the equations of relativity predict infinities, it usually means the theory is being pushed past its domain of validity. Just as Newton's laws fail at speeds close to the speed of light, relativity may fail at the earliest moments of the universe, where quantum effects dominate. The singularity may not be a literal physical point, but a sign that we need a better description. This is where the concept of past incompleteness comes in. Instead of saying the universe had a singular, sharp beginning, cosmologists say that our current models cannot be extended indefinitely into the past. There is a boundary to the reach of relativity, but not necessarily to time itself. Something happened before the universe became hot, dense, and rapidly expanding, but we do not yet know what. Perhaps space and time emerged from a quantum foam. Perhaps the universe bounced from a prior contracting state. Perhaps there was an eternal inflationary landscape, with our universe just one bubble among many. The point is not that the Big Bang was a literal instant of creation, but that it marks the edge of what our current physics can describe. Seen this way, the beginning of the universe is not like the edge of a cliff. It is more like the edge of an old map marked, "Here be dragons." Beyond it, our current equations no longer apply and speculation begins. The Big Bang is not a point in space but a limit in time, the boundary where our mathematical tools fail to reach further. It is also worth emphasizing that a beginning in time does not imply a border in space. Imagine again the balloon analogy. If you rewind the inflation of the balloon, the surface shrinks down, getting smaller and smaller, until it contracts to nothing. The beginning is not a spot on the surface, but the vanishing of the entire surface. In the same way, the early universe was not one point in space, but all of space compressed together. To ask where the Big Bang happened is to miss the point. It happened everywhere. This distinction also helps avoid one of the most common misunderstandings, the notion of the Big Bang as an explosion into emptiness. If that were true, we could identify a central location and measure distances from it. But no such location exists. Every observer in the universe, no matter where they are, can trace their view backward and see the universe converging to the same hot, dense state. The Big Bang is not a place but a state of being, shared by all regions of the cosmos. There is something both unsettling and beautiful in this. Unsettling because it removes the comforting image of a center and a border. Beautiful because it means that the beginning is universal, woven into every particle, every photon, every galaxy. The origin story belongs not to one corner of the cosmos, but to the whole of it. The difference between past incompleteness and a literal origin also shifts how we think about time itself. If time began at the Big Bang, then to ask what came before is like asking what is north of the North Pole. The question presupposes a direction that does not exist. On the other hand, if the Big Bang is only the limit of our equations, then something may indeed have come before, hidden behind the veil of quantum gravity. We do not yet know which picture is true, but both remind us that time, like space, is not as straightforward as our everyday experience suggests. Even if the Big Bang marks the absolute beginning, it is not an edge in space. It is not a rim you could travel toward and reach. It is a moment when the scale factor of the universe, the measure of distances, shrinks to zero. Everything is compressed into a state beyond our comprehension. To say that the universe began there is to describe a time boundary, not a spatial one. Space itself did not exist before that moment in the usual sense. This can be a difficult shift in perspective, but it is also profoundly liberating. The universe does not sit inside a larger container with a wall at the beginning. Its boundary is not like the edge of a book where the story ends, but more like the first page of the book itself, the place where the story starts to be told. Before that page, the book is blank, or perhaps there is another book entirely. Cosmology today is full of attempts to peer beyond this page. Some models suggest that quantum fluctuations created the universe from nothing. Others propose that the universe undergoes cycles of expansion and contraction, bouncing eternally. Still others imagine a multiverse, where inflation keeps spawning new universes with different properties. Each possibility tries to answer what lies beyond the past incompleteness of relativity. None has yet achieved consensus, and perhaps none ever will. But the search itself is part of the wonder, a reminder that even our best theories have horizons. So when you think of the Big Bang, do not picture a firework in empty space. Picture instead a time when all space was gathered together, when the entire cosmos was hot, dense and seething, and when time itself may have only just begun to tick. It was not an explosion into space, but the birth of space. It was not a point in one location, but the state of everywhere. Its edge was not a cliff in space, but a boundary in time, a place where our understanding stops and mystery begins. And perhaps that is the most fitting kind of edge. Not a wall that blocks us, but a horizon that beckons us forward, inviting us to ask what lies beyond even when the answer remains hidden. Black holes are often imagined as cosmic traps, bottomless pits in space wrapped in a shell of impenetrable darkness. The truth is both stranger and subtler. A black hole does not have a hard surface or a fiery rim. There is no solid crust you could knock on with a cosmic hammer. Instead, its defining feature is the event horizon, a boundary that is not made of matter but of rules. The horizon is a one-way curtain, marking the point beyond which nothing, not even light, can return. To understand this curtain, picture yourself falling toward a black hole. From far away, the black hole looks like a sphere of darkness, outlined against the stars. As you drift closer, the pull grows stronger. When you finally cross the event horizon, nothing dramatic happens to you in that instant. No physical wall blocks your way. You glide through smoothly, unaware that you've passed a threshold. Yet from the perspective of the outside world, everything changes. No signals you send, no light you shine can ever make it back across. Your journey has been cut off from the rest of the universe. The horizon is not a surface of stuff. It is a surface of no return. This is why the event horizon is often compared to a stage curtain. From the audience's point of view, anything happening behind the curtain is hidden, no matter how dramatic the performance. The play goes on, but it is sealed from view. In the case of a black hole, the curtain is woven not from fabric, but from the structure of space-time itself. It marks the boundary between regions that can still communicate with the outside universe and those that cannot. In this way, black holes have something in common with the cosmic horizon that surrounds our observable universe. Both horizons mark limits on what can send signals to us. Beyond the cosmic horizon, galaxies continue to exist, but their light cannot reach us because expansion stretches space too quickly. Beyond a black hole's event horizon, objects continue to exist, but their signals cannot reach us because space-time curves too steeply. Both horizons are defined by the paths of light and the rules of causality. They are boundaries in information, not in substance. Yet there are also important differences. The cosmic horizon is about distance and time, shaped by the expansion of space. It grows larger as time passes, gradually revealing more of the universe until dark energy takes over and begins hiding regions again. A black hole's horizon, on the other hand, is tied to mass. The more massive the black hole, the larger its event horizon. It is fixed in place around the singularity at the centre, like a shadow that refuses to shrink. The cosmic horizon may one day fade, but a black hole's event horizon is eternal, as long as the black hole lasts. Another difference lies in what happens inside. Beyond the cosmic horizon, galaxies are still much like the ones we see, with stars and planets, though forever cut off from our contact. Beyond the event horizon, however, space-time itself funnels inward. All paths lead inevitably to the singularity, the central point where densities soar to unimaginable extremes. Once inside, no matter how much you accelerate, every possible future ends at the same destination. The horizon does not just hide what happens, it seals the fate of whatever crosses it. It is tempting to picture the horizon as a surface of material, something that swallows matter like a giant drain. But if you could somehow hover just above it, you would find nothing tangible there. Space does not suddenly stop. Instead, the horizon is a geometric feature, a contour in space-time defined by the paths of light. It is as if the rules of the game shift subtly once you cross the line. Outside, there is always a possible path that leads back to freedom. Inside, every path turns inexorably inward. The edge is in the rules, not in the fabric. From the outside, black holes are surprisingly simple. Einstein's equations tell us that once a black hole forms, it can be described almost entirely by three properties: mass, electric charge, and spin. This is the so-called no-hair theorem, which states that black holes have no additional distinguishing features. All the complex details of the matter that fell in, whether stars, dust, or unlucky astronauts, are erased from the external description. The horizon hides the chaos, leaving only a few measurable traits. This simplicity is part of what makes black holes so mysterious. They are paradoxical objects, defined by what cannot escape, characterized by what cannot be seen. From a distance, they are the most featureless things in the universe, yet inside they may harbor the most extreme physics, where relativity and quantum mechanics clash. The event horizon is the perfect symbol of this tension, an invisible line that both reveals and conceals, marking the point where our understanding falters. There is also a quiet elegance in how nature enforces this boundary. Light itself is the cosmic speed limit. The event horizon is the place where even light's best effort is not enough. A photon aimed outward from the horizon is dragged inward along with everything else. To cross the line is not to hit a barrier, but to reach a point where escape routes vanish. It is a limit written not in stone, but in the geometry of space-time. One of the most fascinating connections between black holes and cosmic horizons is the concept of temperature. Quantum theory suggests that horizons are not entirely silent. They glow faintly with thermal radiation, though at temperatures far too low to detect in most cases. For black holes, this glow is known as Hawking radiation, a slow leak of energy that will eventually cause the black hole to evaporate. For the universe as a whole, something similar applies. The cosmic horizon in a universe dominated by dark energy may also have a temperature, radiating in a way that blends relativity and quantum physics. These hints suggest that horizons, though not made of matter, are deeply physical, tied to the fundamental laws of nature. So when we picture black holes, it helps to let go of the image of a giant cosmic drain with a hard rim. The reality is subtler and in many ways more fascinating. Black holes do not consume space like Pac-Man munching pellets. They reshape space-time so that the horizon becomes a one-way line of no return. From our point of view, it is an edge, but not a physical one, an edge written in the rules of causality. This understanding brings us full circle to the question of cosmic boundaries. Just as the observable universe is limited not by a wall, but by horizons of time and expansion, black holes are limited not by a crust, but by the flow of space-time itself. In both cases, the edges are invisible yet absolute, unbreakable lines that mark what can and cannot be known. They remind us that the universe is not defined by fences but by the laws of physics, laws that sometimes draw curtains where we expected doors. In that sense, black holes are not exceptions to the cosmos but concentrated lessons about it. They show us how space can hide without walls, how boundaries can exist without borders, and how the most dramatic edges are written not in matter but in mathematics. They are horizons without hard shells, quiet curtains drawn across the stage of the universe, where the play goes on beyond sight but never returns to center stage. Imagine a universe emptied of all the clutter of stars, galaxies, and dust, leaving behind nothing but the quiet fabric of space-time itself. Now give that fabric a strange property, a built-in tendency to expand, pushed forward by a constant energy woven into its very nature. That, in essence, is De Sitter space, one of the simplest yet most revealing models of the cosmos. It is a universe dominated entirely by dark energy, expanding smoothly and forever, without the bumps and distractions of matter. At first glance, this sounds sterile, even dull. A universe with no galaxies or stars might not seem worth much attention, but in physics, simplicity can be powerful. By stripping away the complexity of matter, De Sitter space shows us the pure effect of accelerated expansion. It is like studying the tide in the absence of waves or currents, isolating the underlying motion of the sea. In this model, space stretches exponentially, doubling its scale again and again like compound interest running unchecked. One of the most remarkable features of De Sitter space is the presence of horizons. Just as a black hole has an event horizon marking the point of no return, De Sitter space has a cosmic horizon that sets a limit on what any observer can ever see. Beyond that horizon lies an endless universe, but it is hidden forever, sealed away by the rapid expansion. It is not that space ends, but that light from those regions can never outrun the acceleration to reach you. Each observer lives inside a bubble of finite visibility, even though the universe itself has no edges. This horizon creates a curious mix of limitation and serenity. On the one hand, your accessible universe is bounded. You can never see beyond a certain distance, no matter how long you wait, or how powerful your telescope. The curtain of expansion is absolute. On the other hand, what you can see is unchanging in its grand character. The exponential growth smooths away irregularities, leaving a cosmos that looks essentially the same at all times. It is a universe in permanent equilibrium, calm and unhurried, expanding with perfect regularity. In fact, physicists sometimes refer to De Sitter space as the ultimate tractor state, the place the universe naturally drifts toward when matter and radiation thin out. As galaxies move farther apart and dilute, dark energy becomes the dominant force, and the cosmos begins to resemble De Sitter space more and more. It may not be our exact future, but it offers a useful sketch of how an accelerating universe behaves in the long run. What makes De Sitter space especially fascinating is the way it reframes infinity. The universe itself can be endless, stretching without bound. But for you, sitting at some point within it, only a finite portion is ever accessible. Your horizon defines a bubble of experience, a personal cosmos. Beyond it lies infinity, but it is an infinity you can never touch. This creates a strange duality. The universe is both infinite and yet bounded for each observer. The boundary is not material but causal, drawn by the rules of light and expansion. This has profound implications for how we think about knowledge. In De Sitter space, no observer can ever claim to see the whole. Every perspective is partial, limited by horizons. The very structure of space-time ensures that no single view is complete. This humbling fact reminds us that the question, where does space stop, has more than one answer. For the universe itself, there may be no stop at all. For each observer, however, there is always a limit, a point beyond which the universe is hidden, however endless it may be. The serenity of De Sitter space is also deceptive. Though it appears calm, the horizon carries a subtle energy. Just as black hole horizons radiate faintly through quantum effects, so too does the De Sitter horizon. This radiation is extraordinarily weak, far below anything we could hope to measure, but it reveals that horizons are not mere abstractions. They are physical features with temperature and entropy, woven into the laws of quantum mechanics. Even in its calmest state, the universe hums softly with hidden activity. Thinking about De Sitter space can be oddly comforting. It portrays a universe that is self-sustaining, endlessly expanding yet never chaotic, with horizons that protect each observer's view like a cocoon. The stars may fade, the galaxies may drift away, but the fabric itself continues its smooth unfolding. It is a vision of cosmic calm, where change slows and the horizon defines a permanent boundary between the known and the forever unseen. At the same time, De Sitter space is a reminder of how much lies beyond our reach. The hidden regions are not empty, they're just inaccessible. If another observer lived far beyond your horizon, they would see their own bubble of visibility, equally finite, equally serene. The universe would be endless, but no one inside it would ever grasp more than a fraction. Infinity becomes personal, parcelled into private horizons. In practical terms, studying De Sitter space helps scientists understand our own accelerating universe. Observations show that dark energy now dominates cosmic expansion, and the large-scale future may resemble the De Sitter model, more closely with each passing epoch. It offers a way to think about what happens when matter and radiation become negligible, when the universe is ruled entirely by the quiet hand of dark energy. Whether that calm lasts forever or gives way to new physics is still unknown. For now, De Sitter space stands as a model of ultimate balance. Finite horizons set against endless expanses, calm expansion set against the silence of hidden regions. It teaches us that the absence of edges does not mean the absence of limits, and that serenity does not mean simplicity. The universe can be infinite yet veiled, smooth yet mysterious, calm yet profoundly strange. When you look up at the night sky, it is worth remembering that you live in a cosmos gradually moving towards such a state. The galaxies we see today will eventually drift beyond our horizon, one by one, until only the local group remains. The night sky will grow empty, but the universe itself will not have ended. It will simply resemble De Sitter space more and more, serene, expansive, and endless, with hidden regions forever beyond our gaze. In that vision lies a kind of cosmic poetry. The end of contact is not the end of existence. The hidden regions are not erased, only sealed away by the calm expansion of space. De Sitter space shows us that infinity can coexist with limits, and that the universe's most peaceful future may be one where horizons remain, quiet but absolute, forever reminding us that the cosmos is both endless and, in a very real sense, untouchable. When physicists want to talk about the structure of the universe, they sometimes turn to a very curious kind of picture, the conformal diagram, also known as the Penrose diagram. At first glance, these drawings look deceptively simple, often just triangles, diamonds, or squares with a few arrows drawn across them. Yet within these shapes lies an entire cosmos, with infinity folded down into something that fits neatly on a page. It is like bedtime origami for space-time, taking vast expanses and compressing them into manageable patterns without tearing or losing what really matters. The trick of a conformal diagram is that it does not try to preserve distances or sizes the way a normal map would. Instead, it preserves angles and causal relationships. That means light rays always travel at 45 degrees, making it easy to see what can affect what and what lies forever beyond reach. In this way, the diagram turns the complicated geometry of relativity into a clean picture of connections. Horizons, infinities, singularities, all appear as lines you can trace with your finger. Take flat, infinite Minkowski space, the simplest kind of space-time with no curvature and no expansion. On a conformal diagram, it is represented by a diamond. The top of the diamond is future infinity, where all time-like paths end. The bottom is past infinity, where they begin. The sides are spatial infinity, places you can never quite reach, but that are still part of the geometry. Light rays move along the diagonal lines, neatly showing the limits of cause and effect. What looked infinite and unmanageable becomes a finite sketch, without losing the essence of what matters. This approach becomes even more powerful when dealing with curved spacetimes. For a black hole, the Penrose diagram shows the event horizon as a straight boundary line, separating the outside region from the interior. You can see at a glance that once you cross the horizon, all paths lead inevitably to the singularity. For an expanding universe, the diagram shows the cosmic horizon, the region beyond which signals cannot reach us. In both cases, the diagram clarifies what words often obscure, where the edges of knowledge lie, and how they differ from physical edges in space. The beauty of these diagrams is that they compress infinity kindly. Normally, infinity is an overwhelming concept. How do you draw an endless expanse? You cannot. But by stretching and squashing the coordinates, conformal diagrams bring infinity to a finite place on the page. Instead of disappearing off the edge, infinity becomes a boundary within the picture, marked and labelled, part of the structure. It is like taking the endless night sky and painting it on the ceiling of a planetarium dome, not as a deception but as a translation. This also makes it clear why the edges we see in such diagrams are not doors or walls. When you see a line labelled spatial infinity, it does not mean there is a literal wall at that point in the universe. It is a reminder that if you set off toward that direction, you would never stop travelling, never arrive at a final border. The line is a shorthand, a way of saying, here is the unreachable. Similarly, the horizon of a black hole is a line in the diagram, but it is not a shell of material. It is the place where light rays tip inward, shown as a boundary in the picture to remind us of its causal role. In this sense, conformal diagrams are not pictures of the universe the way a photograph is a picture of a landscape. They are more like score sheets for the symphony of space-time, showing how the notes of cause and effect are arranged. They're abstract yet precise, symbolic yet deeply informative, and once you learn to read them, they carry an elegance that ordinary descriptions cannot match. There is also something gently poetic about using geometry to tame infinity. The idea that you can fold endless time and space into a diagram that fits in the palm of your hand feels almost like magic. It recalls the way maps once gave sailors a sense of control over vast oceans, or the way star charts compressed the heavens into a navigable pattern. The conformal diagram is the same, but for the deepest fabric of reality. These diagrams also highlight the relativity of perspective. What looks like a horizon to one observer may not be a horizon to another. In the Penrose diagram, those differences are laid out clearly. You can trace the paths of light rays and see exactly which regions communicate and which remain forever separate. The diagram does not just show the universe, it shows the universe from the viewpoint of causality itself. And causality is what matters most in relativity. Distance can be squashed, time can be stretched, but the chain of cause and effect remains the same. That is why the diagram chooses to preserve angles instead of lengths. The 45-degree light rays are the skeleton of space-time, and the diagram ensures they are always drawn faithfully. Everything else can be reshaped as long as those bones remain intact. In practice, physicists use these diagrams not just for elegance but for insight. They help reveal whether a spacetime is geodesically complete, whether you can extend paths indefinitely, or whether there are true singularities where paths end. They show whether horizons form, whether infinities are time-like or space-like, and how different regions of spacetime fit together. Without them, the equations of relativity would remain forbiddingly abstract. With them, the equations become a picture you can carry in your mind. For those of us outside the physics community, there is still value in these drawings. They remind us that infinity does not have to be frightening, and that boundaries in space-time are not the same as brick walls in space. They show that horizons are features of geometry, not physical barriers. They let us glimpse the structure of reality without demanding that we solve Einstein's equations ourselves. So the next time you see one of those neat little diamonds or triangles labelled with strange symbols, think of it as origami for the cosmos. Infinity has been folded down, horizons have been drawn in, and the story of space-time has been told in a single sketch. The edges are not doors, the boundaries are not walls. They are the footprints of light, the map of causality, the gentle compression of the infinite into something the human mind can hold without being overwhelmed. In that sense, conformal diagrams are not just mathematical tools, but meditations on the nature of knowledge. They show us that infinity can be handled, not by conquering it, but by reshaping our perspective. They remind us that edges in physics are often lines in a diagram rather than limits in reality. And they whisper that, even in the vastness of space-time, clarity is possible, if only you know how to fold the paper just right. When astronomers began mapping galaxies in earnest during the 20th century, they expected to find something like stars scattered across the sky, a fairly even sprinkling, perhaps with a few clumps here and there. What they discovered instead was far more dramatic. Galaxies not evenly scattered but arranged in an intricate pattern of filaments, clusters, and immense empty regions. The result is called the cosmic web, and it is one of the most striking features of the universe on large scales. It looks almost like a neural network, with strands connecting nodes and vast gaps in between. The filaments are enormous chains of galaxies, each link held together by the slow tug of gravity. At the intersections of filaments sit galaxy clusters, cosmic cities containing thousands of galaxies bound in gravitational embrace. These clusters are some of the most massive structures in the universe, glowing with hot gas and teeming with dark matter halos. From a distance, they act as the bright junctions of the web, where matter has gathered most efficiently over billions of years. Between the filaments and clusters lie voids, and these are where the imagination begins to rebel. Voids can be hundreds of millions of light years across, almost entirely devoid of galaxies. When early surveys uncovered these vast gaps, some wondered if they might represent the end of the universe, giant walls beyond which nothing exists. But voids are not cosmic walls. They are not the edges of space. They are simply underdense regions, places where matter did not clump as strongly, leaving behind roomy expanses that are almost but not completely empty. It helps to think of the universe as a vast foam. The filaments and clusters are like the thin walls of bubbles, while the voids are the empty interiors. The foam stretches in all directions, with no boundary where it suddenly ends. Step inside a void and you will not fall into nothingness. You will simply find fewer galaxies around you. The void is not an end, but a quieter neighbourhood in the cosmic city, a place where the streetlights are farther apart. This structure arises naturally from the laws of physics. In the early universe, tiny fluctuations in density, little differences in how matter was distributed, were stretched and amplified by cosmic expansion. Gravity pulled denser regions together, creating filaments and clusters, while emptier regions lost matter to their neighbours, becoming voids. Over billions of years, this process exaggerated the contrast, sculpting the great cosmic web we see today. Despite its intricate appearance, the cosmic web obeys a remarkable rule. On the very largest scales, the universe is homogeneous. That means that if you zoom out far enough, the filaments, clusters, and voids blur together into a uniform whole. Just as a forest looks like a solid green carpet from an airplane, even though it is made of individual trees, the cosmos looks smooth when viewed at scales of hundreds of millions of light years. The web dissolves into a mist of evenness, confirming one of the foundational assumptions of cosmology, that the universe, in the big picture, is the same everywhere. This homogeneity is crucial because it underpins the cosmological principle the idea that we do not occupy a special place in the universe. Our cosmic neighbourhood may be more crowded or more sparse than the average, but when averaged over truly vast distances, every region looks statistically the same. There are no privileged centres, no cosmic walls, no ultimate edges where structure stops. The web is vast but not bounded. Still, it is easy to see how voids might trick us into imagining otherwise. If you lived inside one, with only a handful of faint galaxies dotting your sky, you might conclude that the universe ends just beyond your vision. The night would seem darker, lonelier, perhaps even finite. But if you could travel far enough, you would eventually stumble into a filament, then a cluster, then another void, repeating again and again. The pattern extends, not endlessly proven, but endlessly suggested, leaving no hint of a final wall. The myth of the wall also appears in the way we talk about large surveys. Maps of the universe often display striking boundaries where the data stop, creating sharp outlines that resemble cosmic edges. But these are not walls in nature. They are simply the limits of our instruments. The universe does not cut off at the edge of the map any more than Earth ends at the edge of an old chart marked "Here be dragons." Beyond the surveyed region lies more of the same, waiting to be mapped. What makes the cosmic web especially fascinating is how it connects the smallest scales with the largest. Galaxies form within the dark matter scaffolding of filaments. Stars form within galaxies. Planets form around stars. Life arises on planets. In a very real sense, the structure of the web shapes the conditions that allow us to exist. Without the great filaments channeling matter together, galaxies like the Milky Way might never have formed. The emptiness of voids and the richness of clusters are not just patterns in the sky. They are part of the deep history of how matter organized itself into complexity. And yet, for all its grandeur, the web reminds us that edges in the universe are often illusions. The voids are not endings, but sparse chapters. The filaments are not walls, but strands in an ongoing fabric. Homogeneity assures us that no matter how far we look, the universe retains its balance, smoothing out differences across distance. The cosmic web is intricate without being finite, structured without being walled. From a human perspective, this web is breathtaking. Imagine floating above it, seeing the strands glow faintly with galaxies, the voids yawning vast and dark, the clusters blazing with the energy of billions of suns. It would look like a living structure, a vast neural network pulsing slowly with a flow of gravity. Yet even this grand spectacle is just the middle ground. On smaller scales, galaxies and stars bustle with detail. On larger scales, everything fades into evenness. The web is a fleeting level of organization, neither infinite complexity nor bland simplicity, but something in between. So when we talk about the large-scale structure of the universe, we must resist the urge to imagine cosmic walls or borders. The universe is not built like a fortress, with stone barriers and locked gates. It is built like a web stretching outward in every direction, intricate yet unbounded. The filaments, clusters and voids are not edges but features of a pattern that continues beyond sight. The myth of the wall dissolves under the light of observation. What remains is a cosmos both structured and smooth, intricate and simple, endless in its reach yet uniform in its grand statistics. The cosmic web shows us that boundaries in space are not cliffs but contrasts, not endings but patterns. And in that realization lies one of the universe's most graceful truths. Even its most dramatic structures are part of a fabric that never stops, a tapestry woven without edges. Step outside on a clear night, far from city lights, and the darkness of the sky stretches around you. Pinpricks of starlight glimmer, but they are scattered thinly against an immense black backdrop. To us, this feels natural, even comforting. Night is supposed to be dark, Yet for centuries, thinkers puzzled over a question that seems almost childlike in its simplicity. If the universe is filled with stars, why is the night sky not ablaze with light? This puzzle is known as Olbers's paradox, after the German astronomer Heinrich Wilhelm Olbers, who wrote about it in the early 19th century. But the question was asked long before him, by minds ranging from Johannes Kepler to Edmund Halley. Imagine a universe that is infinite, eternal, and filled uniformly with stars. In such a cosmos, no matter where you look, your line of sight should eventually strike the surface of a star. The entire sky should glow as brightly as the surface of the sun. Night should be as bright as day. Clearly it is not, so what is going on? At first, explanations leaned on the idea of absorption. Perhaps the light from distant stars was blocked by clouds of dust, dimming the sky. But this answer creates its own problem. If the universe were eternal, those clouds would absorb energy until they glowed as brightly as the stars themselves, leaving the night no darker. Absorption alone cannot save the paradox. Something more profound must be at work. The modern solution comes from three intertwined facts. The universe is not infinitely old, the stars are not eternal, and space itself is expanding. First, the universe has a finite age, about 13.8 billion years. That means we can only see light that has had time to reach us since the beginning. Distant stars and galaxies beyond that horizon have not yet had enough time to send their light our way. This immediately limits the brightness of the sky. The universe is not an endless, unbroken chain of stars stretching infinitely into the past. It is a cosmos with a beginning, and that beginning sets a limit on how much light can accumulate. Second, stars themselves do not last forever. Even if the universe were eternal, stars burn for finite lifetimes before fading into embers or collapsing into remnants. The Sun, for example, has a lifespan of about 10 billion years, only a brief flicker compared to eternity. Galaxies are filled with billions of stars, but each one is born, shines, and eventually dies. The night sky cannot be uniformly lit because the supply of shining stars is temporary and staggered. At any given time, only a fraction of all possible stars are radiating. Third, and perhaps most importantly, the universe is expanding. As space stretches, light from distant galaxies is redshifted. Its wavelength grows longer, sliding out of the visible range and into the infrared and microwave bands. This cosmic stretching dims the light before it reaches us, turning what could have been a bright, crowded sky into the faint glow of the cosmic microwave background. Without expansion, the night might indeed be far brighter. With it, the energy of starlight is diluted across longer and longer wavelengths. Together, these three factors, finite age, finite stellar lifetimes, and expansion, resolve Olbers's paradox. The night sky is dark not because the universe is empty, but because it is finite in time, evolving in content and stretching in scale. Darkness is the natural outcome of a cosmos that began, that changes and that grows. What makes this especially elegant is that the darkness of the night sky is not just an absence, it is evidence. Every time you look up at the blackness between the stars, you're seeing a direct consequence of cosmic history. The darkness tells you that the universe had a beginning. It tells you that stars are mortal. It tells you that space itself is dynamic. A dark sky is not a void, but a message written in silence. Even more poetically, the sky is not completely dark. Between the stars lies the faint afterglow of the Big Bang itself, the cosmic microwave background. Invisible to your eyes but detectable with radio telescopes, it fills the heavens with a whisper of radiation left over from the early universe. The black canvas of night is painted with an invisible wash of ancient light. Far from being empty, it is the most eloquent darkness we could imagine. Some philosophers once used the darkness of the night sky to argue that the universe must be finite in space. After all, if it were infinite, would it not be bright? But the modern solution shows that infinity is not the problem. Even an infinite universe can have a dark sky, so long as it has a finite age and is expanding. The darkness does not require edges. It requires history. It requires time. This realization reframes the way we think about night itself. When you gaze into the dark sky, you're not looking at emptiness. You're looking at distance, at time, at the limits of light's long journey. The quiet is not the quiet of absence, but of patience. The patience of photons stretched thin over billions of years. There is a quiet poetry in the fact that our ancestors, wondering why the sky was dark, were stumbling toward one of the greatest truths of all. The universe had a beginning. They did not yet know about the Big Bang or redshift or stellar evolution, but their question carried the seed of those discoveries. The darkness of night is a clue as fundamental as any experiment in a laboratory. And perhaps that is the most comforting conclusion of all. The night sky is dark not because the cosmos is small or because it has edges, but because it is vast, dynamic, and alive with history. Its darkness is full of meaning. It is the kind of darkness that whispers stories rather than silences them, a darkness that invites us to listen rather than to despair. So next time you find yourself beneath the stars, let the quiet of the sky wash over you. Remember that the darkness is not emptiness. It is a record of beginnings, of endings, of expansion, of change. It is the visible proof that the universe has a past and a future, and that our place in it is one moment in a much larger unfolding. Night is not just the absence of light, it is the presence of a story, a cosmic story written in darkness, stretching across time without the need for walls or edges. When you stand beneath the stars, it is natural to wonder just how far the universe really goes. The observable cosmos stretches about 92 billion light-years across, but that figure only tells us how much light has had time to reach us since the Big Bang. It says nothing about how far the universe extends beyond what we can see. So how big is the whole thing? Could it be just a little larger than our visible patch, or could it be truly infinite? One of the challenges in answering this is that we only ever have one universe to observe. Unlike a scientist who can repeat an experiment, cosmologists are stuck with a single data set, the sky above us. This introduces what is called cosmic variance, the unavoidable uncertainty that comes from only having one view. We can measure the distribution of galaxies, the patterns of the cosmic microwave background, and the geometry of space in exquisite detail, but we cannot peek beyond the cosmic horizon to check whether the rest looks the same. Our best estimates of the universe's size are therefore lower bounds. It must be at least this big, but it could be far bigger. So what do current measurements tell us? One key clue comes from the curvature of space. If the universe is positively curved like the surface of a sphere, it must be finite. If it's flat or negatively curved, it could be infinite. Measurements of the cosmic microwave background, especially by the Planck satellite, suggest that the curvature is very close to flat, with any deviation smaller than about 1 part in several hundred. This means that if the universe is finite, its size must be enormous, at least hundreds of times larger than the observable patch, perhaps much more. From our perspective, it looks indistinguishable from infinity. Another clue comes from the distribution of a large-scale structure. Galaxies are arranged in filaments and voids, but when you zoom out far enough, the universe becomes homogeneous. It looks the same in all directions and in all regions we can observe. If there is an edge not far beyond our horizon, it leaves no trace in the structures we see. The smoothness suggests that whatever lies beyond is not radically different. at least not until distances vastly greater than those we can probe. This brings us to an important distinction: the difference between conclusion and constraint. Scientists cannot conclude from the evidence that the universe is infinite. Infinity is not something you can measure directly. What they can do is place constraints, showing that the universe must be at least a certain size. It is like walking into a forest, seeing trees stretch as far as the eye can see, and saying, "The forest is at least this big." Whether it ends a few hills away or continues without limit remains uncertain. Cosmic inflation complicates this picture in an interesting way. Inflation suggests that in the very early universe, space expanded at an exponential rate, smoothing and flattening everything. In most models, this expansion would make the universe vastly larger than the observable region. Some versions even imply that the universe could be truly infinite. Others allow for a finite but extremely large space, perhaps folded back on itself in complex ways. Inflation tells us that the observable patch is only a tiny fraction of the whole, but it does not tell us the exact scale of the stage. So where does that leave us? With a universe that is at least unimaginably vast and possibly without end. The observable cosmos, as large as it is, may be only a speck in a larger expanse. If the universe is finite, it is so large that light has not yet had time to reveal its closure. If it is infinite, then no amount of waiting will ever reveal an edge, because there is none to be found. It is humbling to realize that we may never know for certain. Our telescopes, however powerful, are limited by the speed of light and the age of the cosmos. The horizon is not just a technological barrier, it is a fundamental boundary of information. Beyond it, the universe may continue exactly as before, or it may curve back on itself. We cannot see far enough to decide, but uncertainty does not mean ignorance. The very fact that we can set such enormous lower limits is itself astonishing. From ripples in ancient light, we can infer that the universe is at least hundreds of times larger than the region we observe. From the smoothness of the cosmic microwave background, we can infer that the cosmos is remarkably uniform, suggesting no nearby walls or edges. From the success of inflationary models, we can infer that our observable patch is a small slice of a much grander whole. These are constraints, not conclusions, but they are powerful ones. The question of size also ties into the deeper philosophical question of infinity. If the universe is infinite, then there may be infinite galaxies, infinite stars, and even infinite copies of you scattered across the expanse. If it is finite but enormous, then the number is still staggering, but at least countable in principle. Infinity is a slippery concept in physics, often treated with caution. Whether or not it applies to the cosmos itself remains an open question. Perhaps the most poetic answer is that the universe is big enough to contain galaxies and clusters and webs of matter stretching across billions of light years, big enough to harbour life on at least one small planet and perhaps countless others, big enough to baffle our imaginations and stretch our mathematics to the limit. Whether it is finite or infinite, the cosmos is already more immense than anything else we know. So when we ask, how big could the whole universe be? The honest answer is that it could be finite, it could be infinite, but either way, it is far beyond the boundaries of our observable bubble. The difference lies not in what we see, but in how far the unseen stretches. Constraints tell us it is vast beyond comprehension. Conclusions remain elusive. There is a quiet beauty in this uncertainty. The universe has shown us enough to know that it is vast, smooth, and ancient, but it has hidden enough to keep us humble. The horizon stands as both a limit and an invitation, a reminder that knowledge always comes with boundaries. The size of the cosmos may be unknowable, but its immensity is certain, and perhaps that is enough. to know that we live in a universe so large that even our best instruments cannot trace its edges, a cosmos that outpaces not just our reach, but our imagination. Imagine a universe that does not go on forever, but instead loops back on itself. A cosmos where travelling in a straight line long enough could, at least in principle, bring you back to where you started. Not because you curved around a planet or orbited a star, but because space itself is stitched together in such a way that straight paths eventually close. This is the idea of a finite but unbounded universe, a wraparound world where the edges are hidden by the very fabric of geometry. What would life be like in such a cosmos? For one thing, the night sky might contain hidden repetitions. If light can circle all the way around, you could, in principle, see your own galaxy appearing in multiple places in the sky. Imagine peering through a telescope and spotting the Milky Way not just from the inside, but also from the outside, a ghostly double of our home swirling at a distance. That would be the ultimate cosmic selfie, the galaxy seeing itself from behind after its light completed a cosmic lap. Everyday astronomy in such a universe would be full of fascinating surprises. Galaxies could appear in duplicate, triplicate, or more, each one a copy of the same object viewed along different light paths. They would not look identical, though, because light takes time to travel. One image might show the galaxy as it was billions of years ago, while another reveals it in a later stage of its evolution. Astronomers would have the strange privilege of watching the same galaxy grow old in several parts of the sky. So far, no such repeats have been observed. Surveys of galaxies and maps of the cosmic microwave background have searched for these telltale signatures. If the universe is small and compact, repeated patterns, sometimes called matched circles, should show up. Yet the sky has revealed no clear evidence of such looping. This suggests that if the universe is finite, its size is at least larger than the observable region. In other words, the cosmic wraparound may exist, but the loop is so vast that light has not yet had time to complete a full circuit and return to us. Still, the thought experiment is irresistible. What would it mean to live in a wraparound cosmos? For one, navigation would be very different. Imagine trying to send a probe outward in one direction, only to have it eventually return from behind. The cosmos would feel both boundless and strangely enclosed, infinite in experience but finite in fact. The concept of far away would lose some of its meaning, because every path eventually circles back. This also reshapes the way we think about infinity. In a finite wraparound universe, the number of galaxies could be limited, but the number of times you could encounter them would be unending. You could see the same structures repeated endlessly across the sky, each one a different moment in time. Infinity arises not from size, but from repetition. The cosmos becomes a hall of mirrors, reflecting itself again and again through the geometry of space. For sleep-friendly thought experiments, picture yourself drifting through such a universe. You set off in a straight line, moving at a constant pace. For millions of years you pass galaxies and clusters, always moving forward. Then, one day, without ever turning, you see familiar constellations ahead. Slowly it dawns on you. You have returned to your starting place. The journey was not circular in the ordinary sense, but circular in the fabric of space itself. The universe is a loop and you have just traced it. Or imagine lying under the night sky, wondering whether the stars you see are truly different, or whether some of them are echoes of the same places viewed from another angle. The thought has a strange kind of comfort. It means that the universe does not need to be infinite to feel endless. It only needs to be connected cleverly enough that the journey never stops. Of course, such a cosmos would raise practical questions for astronomers. How would we distinguish duplicates from genuinely different galaxies? One way would be to look for suspiciously similar structures in different parts of the sky. But galaxies evolve, so the images would never be exact. Another method would be to search for repeating patterns in the cosmic microwave background, the leftover light from the Big Bang. That light should also wrap around, creating symmetrical imprints. The absence of these signals so far means that if the universe is finite, its wraparound is very large. Yet even without evidence, the idea serves a valuable purpose. It reminds us that our intuitions about edges and infinities are not always trustworthy. The universe does not need a wall to be finite, and it does not need infinity to feel boundless. Geometry alone can create a cosmos that is both complete and unending. For a calming perspective, think of it this way. The universe is like a story that repeats but never quite the same way twice. Each repetition is another chapter, another view, another time. The wraparound does not cheapen the vastness of the cosmos, it enriches it with layers of connection. Infinity hides not in endless size, but in the endless possibility of return. And in the end, whether space truly loops back on itself or stretches without limit, the experience from our tiny corner is the same. The night sky is full of mysteries, many of which may be echoes, and many of which may be beyond reach forever. Living in a wraparound world would be strange, but perhaps not so different from living in this one. A cosmos where the edges are elusive, where the paths are long, and where the stars keep us wondering whether space ever really stops. Infinity is one of those words that rolls easily off the tongue but resists every attempt to be pinned down. When people imagine an infinite universe, they often picture it as a kind of endless plane, stretching without limit in every direction. But infinity is not really a place you can walk to. It is a property, a way of saying there is no end. If space is infinite, it does not mean that somewhere very far away you will bump into the edge of infinity itself. It means that no matter how far you go, there is always farther still. This idea has fascinated and unsettled humans for centuries. An infinite cosmos means that galaxies and stars continue forever, without boundary or closure. It is a vision of gentle vastness, not an explosion of fireworks, but a quiet continuation, on and on, with no need for walls. From a philosophical perspective, it is oddly calming. There is no edge to fall from, no outer void waiting beyond. Space simply is, with no requirement for stopping. One popular claim is that in an infinite universe, everything repeats somewhere. The logic goes like this. If there are only so many ways to arrange matter, then eventually, given infinite space, every possible arrangement must occur again. Somewhere, unimaginably far away, there would be another Earth, another you, perhaps even listening to these same words. The idea is both whimsical and unsettling, conjuring visions of infinite copies living out every possible variation of existence. But this claim, while catchy, is slippery. It confuses mathematical infinity with physical prediction. Infinity by itself does not guarantee repetition. It depends on whether the universe truly has a finite number of possible states, whether the physics of matter and energy allow only certain configurations. If the possibilities are infinite too, then space could stretch forever without ever repeating exactly. An infinite cosmos may not be a hall of mirrors filled with duplicates, but something stranger, endless variety without closure. It helps to recall that infinity in mathematics often describes a limit rather than a literal quantity. The set of whole numbers is infinite, yet no number is ever repeated. Infinity means unending continuation, not guaranteed duplication. The same distinction may apply to space. The universe might extend without limit, filled with galaxies forever, but that does not mean those galaxies must repeat. The property of infinity is not the same thing as a pattern that circles back. This distinction matters because it grounds our imagination. Infinity is seductive, but physics demands caution. When cosmologists speak of an infinite universe, they usually mean that current measurements of curvature and expansion do not require a finite boundary. They mean that models allow for endless extension. But whether that infinity is realized in nature, and whether it brings repetition with it, are questions far beyond what telescopes can answer. For now, infinity remains a hypothesis, not a conclusion. And yet, even as a hypothesis, it carries a quiet grandeur. Imagine stepping outside on a dark night and knowing that no matter how far the stars extend, there is always more beyond. The sky becomes not just a dome over your head, but a window into a depth without bottom. Infinity is not loud or dramatic. It is gentle, a vastness that simply continues, indifferent to boundaries. There's also something strangely reassuring about living in an infinite cosmos. It means that existence is not precariously balanced on the edge of a cliff. There is no border beyond which nothingness looms. Instead, there is always more sky, more galaxies, more structure. The infinite is, in a way, the ultimate comfort zone, a universe that never stops offering more. At the same time, infinity can be intimidating. Some people find the thought overwhelming, as though the self shrinks to invisibility against the backdrop of endlessness. But there is another way to look at it. Infinity does not erase our place, it frames it. Just as a single note still matters within an endless piece of music, so too does a single planet or a single life matter within an infinite cosmos. The vastness does not diminish the melody, it makes it richer. Infinity also challenges the way we think about science. In the lab, we rely on experiments that can be repeated, outcomes that can be checked. With infinity, we encounter something that cannot be tested in the same way. No matter how far we look, we can never confirm the absence of an edge, because we can never see all of space. Infinity remains a concept at the border between mathematics and physics, half rigorous and half philosophical. That tension can be unsettling, but it is also where the beauty lies. Infinity invites us to stretch our minds, to hold an idea that cannot be pictured in full, but can still shape how we think. It reminds us that the universe does not have to conform to our desire for closure. It may be infinite, and if so, it will remain forever beyond the reach of final comprehension. For a gentle thought experiment, picture yourself drifting through such a universe. You sail past galaxy after galaxy, never reaching an edge, never circling back to the beginning. Each cluster of stars is unique, each arrangement new. The journey never ends, but it also never needs to. There's always more horizon, more night, more quiet continuation. The infinity is not oppressive but soothing, like a path that invites you to walk without ever worrying about the destination. So if space is infinite, what does that mean for us? It means the night sky is not a ceiling but a boundless expanse. It means there are no walls to hem us in, no rims to fall over. It means that questions of repetition or duplication are less important than the deeper truth. Infinity itself is a property of the cosmos, a reminder that not everything must end. And perhaps the greatest lesson is that infinity does not have to frighten us. It can be gentle, a vastness that does not demand understanding but offers perspective. It reminds us that our lives, though small, are part of a canvas without edges. The universe may be infinite, or it may only be unimaginably large. Either way, it invites us to rest in the knowledge that there is no sharp stop to space, only an openness that stretches beyond sight, quiet and unending. Infinity, then, is not a place to find, but a way to think. Not a destination, but a property. If space is infinite, it is not a mirror of ourselves, but a calm vastness in which our questions echo. And if that thought accompanies you as you drift towards sleep, perhaps it can turn the intimidating into the soothing. A universe without walls, a horizon without end, a gentle infinity that simply is. The word multiverse has a way of slipping into conversations about cosmology like an uninvited but intriguing guest. It conjures images of countless universes stacked together, each with its own stars, galaxies, and perhaps even versions of ourselves living out different lives. But what does this idea actually mean when treated carefully, in the language of physics rather than science fiction? At its core, the multiverse is not a single theory but a family of ideas, most of which grow out of attempts to explain how our own universe came to be. One of the leading versions is called eternal inflation. Inflation, as we have seen, was that blisteringly fast expansion thought to have happened in the first fraction of a second after the Big Bang. In most models, inflation ends everywhere at once, leaving behind the hot, dense universe we observe today. But in some versions, inflation is not a one-time event. Instead, it keeps going in some regions while stopping in others. Where it stops, a bubble universe forms, like a pocket of steam in boiling water. Where it continues, space keeps stretching. The result is a frothy landscape of bubble universes, each with its own physical conditions, separated by eternally inflating space. In this picture, our universe is just one bubble among many. We see only the interior of our bubble because the walls separating it from others are impassable, inflated away faster than light could ever cross. Each bubble could have different values for the constants of nature, different arrangements of matter, even different dimensions of space and time. The multiverse, then, is not a collection of universes side by side in some larger room. It is a patchwork generated by an ongoing process, with new bubbles forever forming. Other multiverse ideas come from string theory. String theory, which attempts to unify all the forces of nature into one framework, allows for a staggering number of possible solutions, sometimes called the string landscape. Each solution corresponds to a possible universe with its own laws of physics. If inflation can populate that landscape, then the multiverse could be unimaginably diverse, with universes where physics looks nothing like our own. All of this is provocative, but what could ever count as evidence? After all, by definition, other universes are beyond our observable horizon. We cannot point a telescope at them, nor can we hope to send a probe across the inflating space that separates us. Yet scientists have speculated about indirect hints. For instance, if another bubble collided with ours in the distant past, it might have left an imprint in the cosmic microwave background, like a bruise on the sky. Some researchers have even searched for such features, subtle circles or anomalies in the CMB data, but so far nothing definitive has been found. Another form of evidence could be more philosophical. If the constants of physics in our universe seem finely tuned to allow for life, one way to explain this is through selection. In a multiverse with many variations, we happen to find ourselves in a universe where conditions permit our existence. This does not prove the multiverse, of course, but it makes the idea appealing to some, as it shifts the question of fine-tuning from why here to why not somewhere. Still, it is important to handle these ideas with care. The multiverse is not a solution to the question of edges, it merely shifts the question to a bigger scale. If our universe is just one bubble in a vast froth, what contains the froth? If inflation is eternal, what set it in motion? If the landscape of string theory generates universes, what explains the landscape itself? The multiverse does not abolish mystery, it multiplies it. The edges are not erased, but reframed, hidden inside a deeper layer of questions. This is why some physicists remain cautious. A theory is most useful when it makes predictions that can be tested. The multiverse, by its nature, resists that. It offers a compelling narrative, but one that hovers at the boundary between science and philosophy. It is not dismissed outright. After all, it is a natural outgrowth of serious physics, but it is not embraced as proven either. It occupies a twilight zone of speculation, where imagination and mathematics meet. For a gentle way to think about it, imagine standing on a shore, looking out at the ocean. You can see only as far as the horizon, but you know the sea continues beyond it. Now imagine that beyond your horizon there are other islands, each with its own inhabitants, each with its own weather. You will never visit them, but their existence is not impossible. The multiverse is a cosmic version of this thought. Perhaps our universe is one island in a larger sea, one bubble in a broader froth, and yet, whether or not the multiverse is real, our universe remains wondrous enough. The stars, galaxies, and cosmic web already stretch farther than we can reach. The cosmic microwave background already carries whispers from nearly 14 billion years ago. Infinity itself already hovers as a possibility. We do not need countless universes to feel awe. One is already more than enough. So when we speak of the multiverse, it helps to keep two thoughts balanced. On the one hand, it is a serious proposal, born from real physics like inflation and string theory. On the other hand, it remains speculative, with little direct evidence to anchor it. It is an idea to be explored, not yet a fact to be embraced. In this light, the multiverse can be seen less as an answer and more as an invitation to imagine, to extend the questions of cosmology beyond what we can observe, and to recognize that even our most daring theories leave mysteries untouched. If there are other universes, they do not diminish ours. They only add to the wonder, making the cosmos an even larger, stranger, and more beautiful place. And if, in the quiet of night, your thoughts wander to the possibility of countless other worlds, take comfort in knowing that whether they exist or not, the one you live in is already vast enough to keep you in awe for a lifetime. The multiverse is not required for wonder. It is simply another way the universe teases us with the possibility that reality may be richer than we can see. There is a quiet lesson tucked into the practice of cosmology, one that often gets overshadowed by the dazzling images of galaxies and the bold headlines about discoveries. The lesson is that much of what we know about the universe is wrapped in uncertainty. Not the careless kind, but the precise, measured uncertainty that scientists carefully cultivate. It is a humility built into the fabric of observation itself. When we point our instruments at the cosmos, we are not seeing the universe directly. We're interpreting signals, photons captured by detectors, radio waves filtered through antennas, subtle patterns turned into numbers. Each step in that chain has its own limitations, its own whispers of noise. Cosmic variance, for example, is not just a technical phrase. It is a reminder that we only have one universe to look at. We cannot repeat the experiment with a dozen universes and compare the averages. Our sky is a single sample, and so every measurement is subject to the randomness of that one cosmic lottery. Consider the cosmic microwave background, that faint afterglow from the early universe. Satellites like COBE, WMAP, and Planck have mapped it with extraordinary precision, down to fluctuations in temperature smaller than 1/100th of a degree. But even these maps are limited. They show one realization of the universe's early conditions, ours. Somewhere, in another universe, if such things exist, the pattern might be different. We cannot compare. We must accept that our data come with cosmic variance, a kind of built-in uncertainty that no improvement in technology can erase. Beyond variance, there are the practical limits of instruments. Telescopes are bound by the size of their mirrors, the sensitivity of their detectors, and the interference of their environment. Even in space, free from atmospheric distortion, instruments encounter noise, the faint crackle of electronics, the slow creep of heat, the statistical randomness of photon arrival. Astronomers spend as much time subtracting these imperfections as they do analysing the signal itself. The universe is vast, but the information it offers arrives as a trickle, always accompanied by static. This is why scientists speak so often of error bars. An error bar is not an admission of failure, it is a badge of honesty. It tells you the range within which the truth almost certainly lies. When you read that the universe is 13.8 billion years old, that figure comes with uncertainties, plus or minus a few tens of millions of years. That sliver of doubt is not weakness, it is strength. It shows that the measurement is precise enough to know where the uncertainty begins. The absence of evidence is another point worth lingering on. In everyday life, we often treat absence of evidence as evidence of absence. If something is not seen, we assume it is not there. But in science, especially at the scale of cosmology, absence of evidence often means only that our instruments were not sensitive enough, or that the signal was too faint, or that it lies just beyond our horizon. The silence of the night sky does not prove the universe has an edge. The lack of repeating patterns does not prove the universe is infinite. It simply reminds us of the limits of our reach. There's a gentleness in learning to live with this. The universe does not reveal itself all at once, and perhaps it never will. Knowledge comes in increments, surrounded by uncertainty, shaped by the boundaries of measurement. To demand final answers is to misunderstand the nature of discovery. To appreciate the precision of uncertainty is to accept that science is less about endings and more about horizons. At bedtime pace, this perspective is soothing. Imagine the cosmos as a book written in faint ink. Each page reveals some words clearly, while others fade into smudges. You can read enough to follow the story, but the missing lines remain tantalizingly out of reach. The temptation is to fill them in yourself, to declare what must be written there. But the wiser path is to pause and acknowledge the gaps, to appreciate the story we do have, even with its omissions. This humility is not defeatist. On the contrary, it is what makes cosmology resilient. By embracing uncertainty, scientists prevent themselves from leaping to false certainties. When new instruments arrive, they refine the picture. When new data come in, they adjust the models. The progress of cosmology is like sketching with a pencil. Outlines first, details later, always with room for correction. The eraser is as important as the lead, and sometimes the uncertainty itself is more revealing than the data. For instance, when measurements of the Hubble constant, the rate of cosmic expansion, differ depending on how you measure it, that discrepancy is not just noise. It might be a clue that something deeper is missing from our understanding. The tension between numbers becomes an invitation to look again, to wonder whether new physics waits just beyond our models. In this sense, the limits of knowing are not walls but doorways. Each boundary of measurement points toward a possible opening. Cosmic variance tells us we may never know everything, but it also tells us exactly where the edge of certainty lies. Instrumental noise reminds us of imperfection, but it also drives the invention of better detectors. Uncertainty may sound like vagueness, but in practice it is sharp, disciplined, and essential. There is comfort here too. You do not need to solve every mystery before sleep. The universe itself holds mysteries close, revealing them slowly, always framed by uncertainty. What we know is precious precisely because it comes wrapped in limits. The quiet honesty of error bars and confidence intervals is its own kind of beauty. So as you listen to the hum of the cosmos through our imperfect instruments, remember that precision does not mean perfection, and uncertainty does not mean ignorance. It means we are learning carefully, humbly, patiently. The universe may never tell us where it ends, or whether it ends at all, but in the silence between answers there is room to wonder and room to rest. When humans try to grasp the immensity of the universe, we often reach for metaphors. We compare space to balloons, to bread dough, to ocean waves, or to the surface of a sphere. These images are like stepping stones, helping us cross the river of abstraction. Without them, the mathematics of cosmology can feel like a language without translation. But metaphors are double-edged. They help us imagine, but they can also mislead, sneaking in assumptions that do not quite match the reality. Take the balloon analogy. You may have heard it before. Galaxies are like dots on the surface of a balloon as it inflates, all moving farther apart as the surface stretches. It is a useful image for metric expansion. No galaxy is at the centre. All drift apart as the fabric of space grows. Yet balloons have an inside and an outside, and people often imagine the universe as a balloon expanding into some larger void. The truth is strange. The universe does not need an outside to expand into. The balloon analogy carries that hidden baggage, which can quietly distort the picture. Or consider the raisin bread metaphor. Galaxies are like raisins in dough as it rises, carried farther apart by the swelling bread. Again, this captures the essence of expansion. But bread has edges. It exists in an oven, on a tray, in a kitchen. The universe has no such external container. The image comforts us by tying the cosmic to the familiar, but it risks shrinking the strangeness of reality into something too domestic. Even the phrase Big Bang as a metaphor, and not a particularly accurate one. It suggests an explosion in space, with matter rushing outward from a central point. In fact, the Big Bang was not an explosion at all, but the rapid expansion of space itself, everywhere at once. There was no centre, no outside. The metaphor of a bang captures the drama but obscures the subtlety. At night, when the mind is quiet and seeking rest, metaphors can be both soothing and troublesome. They give us pictures to hold on to, but if those pictures are too concrete, they may lead us to wrestle with questions that don't quite make sense. Asking, what is the universe expanding into, is a natural follow-up to the balloon image, but the question itself dissolves once you realize the metaphor's limits. The balloon has an outside, the universe doesn't need one. The metaphor got us partway there, but it smuggled in an unnecessary puzzle. Perhaps what we need are gentler, clearer images, metaphors chosen not to impress with drama, but to guide with calm precision. Instead of a balloon in a room, imagine the surface of Earth itself. Walk in a straight line and you never find an edge. You only loop around. This image at least captures the idea of finite yet unbounded, without introducing an outside. Or picture ripples spreading on a pond, not because the pond is exploding, but because the ripples themselves are stretches of water. These analogies are not perfect either, but they mislead less. Even more helpful than metaphors are better questions. Instead of asking, where does space stop, we might ask, what are the limits of what we can see? That question has an answer. The observable universe, bounded by the age of light travel. Or we might ask, what shapes could space have? That leads us to curvature and topology, concepts we can probe with real measurements. The shift from stop to shape, from edge to horizon, transforms the puzzle into something answerable, or at least approachable. This reframing is not about deflating wonder. If anything, it deepens it. To ask whether the universe has an edge is to invite disappointment, because physics suggests the answer is no. No wall, no rim, no final cliff in space. But to ask how horizons limit us, how geometry bends, how infinity might or might not apply, that opens doors to a richer, subtler wonder. These questions acknowledge both what we know and what remains beyond reach. At bedtime pace, this reframing has a gentle quality. Instead of battling with the impossible picture of a wall at the end of space, you can rest in the thought of horizons, expanding webs and smooth curvatures. The metaphors become softer, more like lullabies than puzzles. Space is not a fortress to escape, but a landscape to wander, with paths that stretch farther than sight. The mystery is not a locked door, but a misty horizon. It is also worth remembering that language itself evolves. Terms like dark energy and cosmic web are metaphors too, chosen to evoke images while pointing at phenomena that remain abstract. Dark energy is not literally dark, nor is it an energy in the ordinary sense. The cosmic web is not spun by any spider. These words are bridges, not destinations, scaffolds for thought that will eventually be replaced or refined. Our understanding of the universe is always filtered through metaphor, but the best metaphors are the ones that remind us of their own limits. In the end, perhaps the most restful approach is to hold the metaphors lightly. Let them be images that guide without binding, tools that sketch but do not define. The universe is too strange to fit neatly into any picture, but that strangeness need not be unsettling. It can be calming, a reminder that not every question has to resolve into an answer before sleep. So instead of asking where does space stop, you might ask, how does space shape what I can see? Instead of picturing walls, you might picture horizons. Instead of demanding finality, you might rest in possibility. In that shift, the metaphors become softer, the questions become gentler, and the night sky becomes not a problem to solve but a mystery to embrace. And if these questions drift with you into dreams, let them be not heavy puzzles, but light companions, reminders that the universe is vast, language is flexible, and the best answers are often found in the reframing of the question itself. If you have carried these thoughts with you through the night, the picture that emerges is gentler than the word edge suggests. Space is not a box with walls, nor a stage with curtains you can draw back to step outside. It is a fabric of relationships, distances and durations, paths for light and for influence, shaped by gravity, stretched by expansion, and stitched together by causality. When we ask where it stops, we are really asking where our connections stop. And the honest answer is that what ends is not space itself, but our ability to see farther or to be seen. Horizons are the clearest expression of this. They are not barricades, but boundaries in the flow of information. The past light cone gathers all that has had time to reach us. The future light cone contains everywhere our signals can ever go. The observable universe is the portion of the cosmos that has stepped inside our past cone since the beginning. Beyond that, nothing sudden happens. No cliff, no wall, only a quiet absence of messages. On still larger scales and in the deep future, accelerating expansion draws another horizon, regions that continue to exist but will never speak with us again. The universe does not end there. Only the conversation ends. Curvature gives this silent shape without erecting borders. A positively curved space can be finite and unbounded, like the surface of a sphere extended to 3 dimensions. A flat or negatively curved space can be infinite, extending without limit. In each case, edges replaced by geometry. Triangles sum to more or less than 180 degrees. Parallel lines meet or diverge. Straight paths may loop or run on forever. None of these geometries demands a rim. The shape of space tells us how journeys behave, not where they must stop. Topology goes a step further and asks how space is connected to itself. It allows for a cosmos that wraps around, where straight lines eventually return to their starting point, and where a small, finite universe can be complete without any outside. In such a world, repetition is possible in principle, distant copies of structures, light returning by different routes. Yet the absence of obvious repeats so far simply tells us that if this wraparound exists, its scale surpasses our horizon. Again, no wall is needed. A clever stitching of space can remove borders by never creating them. The map that makes these ideas tangible is the cosmic microwave background, an ancient light that shows us the universe when it was young. Its delicate ripples carry clues to curvature, to the seeds of structure, and to possible topological signatures. Their very subtlety is a lesson in limits. What we infer about the whole rests on patient readings of a faint pattern on the sky. From this light we learn that our patch is nearly flat and remarkably uniform, and that if there are twists and loops they lie beyond the portion we can survey. The message is not that there is nothing beyond, but that we have not yet seen it, and may never. Inflation, that brief and breathtaking early expansion, explains much of this calmness. It irons the fabric smooth, sets the scale of our visible patch, and scatters quantum seeds that later unfold into galaxies and filaments. Yet even inflation refuses to answer whether the whole is finite or infinite. It widens our stage without showing the theatre's outer walls, if any exist. Dark energy, emerging later, adds the final, quiet touch. A gentle acceleration that turns horizons into lasting farewells. In time, many galaxies will simply slip out of our future light cone. They will not cease to be, they will cease to be reachable. These themes, horizons, curvature, topology, and the limits of observation, converge on a single soothing understanding. Space likely has no hard edge. There is no cosmic cliff where stars give way to nothing. There are horizons that mark the ends of contact. There are geometries that guide the ways paths bend and the ways light travels. There are possible global connections that remove borders by looping the fabric back upon itself. And there is the quiet honesty of measurement, a recognition that our view is one view, framed by time, filtered by instruments, softened by noise, bounded by cosmic variance. This humility is not a defeat. It is a kindness to the mind. It says, you're allowed to rest without solving everything. Absence of evidence, no matched circles, no repeating sky, does not demand the conclusion of absence. It invites patience. Error bars are not cracks in knowledge. They are the frame around it, showing exactly where certainty ends and wonder begins. The universe meets us halfway. Enough light to learn, enough darkness to dream. Language, too, becomes gentler when we let it. Instead of explosions and rims, we speak of expansion and horizons. Instead of edges, we imagine shapes. Instead of outsides, we consider connections. The metaphors soften. The universe is a fabric, not a fortress, a landscape, not a room. The questions soften with them, not where does space stop, but how does the structure of space limit what we can observe and influence? Not what lies beyond the wall, but what geometry, what topology, what horizon sets our present circle of light. And so the calm takeaway settles in. What ends is not space, what ends is contact. The universe may be infinite, or finite and without borders. In either case, the edge we feel is the edge of our reach, the place where light from distant regions has not yet arrived, or will never arrive, and the place beyond which our own signals will never be heard. That edge moves with time as the cosmos expands. Sometimes it reveals more, sometimes it withdraws. Always it is written in the rules, not in a wall. Hold then one last image for sleep. Picture yourself at the centre of a quiet night, and imagine an ever-widening circle of light centred on you, expanding at the speed of light, touching new places with each passing moment. Within the circle is the knowable, stars that have already spoken to you, galaxies whose whispers have crossed the dark. Beyond the circle is not a barrier but a waiting. Regions that will one day speak, and others that will remain forever silent. Not because they are not there, but because the current carries them away faster than messages can arrive. The circle grows, it never meets a wall. It only meets the limits of time and the gentle rules that guide light. Far ahead, the darkness is patient. It is not emptiness, it is possibility. The fabric continues. Curved or flat, looped or open, whether you see it or not. And as the circle widens and your eyes grow heavy, you can let the question of endings loosen its grip. There is no rim to fear, only horizons to acknowledge, only a vastness that keeps its distance with grace. Sleep with that circle in mind, a soft expanding glow in a darkness that is not a void but a hush. Beyond tonight's horizon, the universe waits, unwalled, unhurried, and very likely endless to our touch.